In this video, we're going to be breaking down 100 facts about the Mariana Trench, from its incredible depths to the mysterious creatures that call it home. The Mariana Trench sits in the western Pacific Ocean like a massive underwater scar, stretching about 200 kilometers east of the Mariana Islands. Picture this: if you were floating above it, you'd be roughly 124 miles from Guam, that US territory you might know from the news. The trench curves through the ocean in a crescent shape, almost like a giant smile turned sideways, measuring an impressive 550 kilometers long. That's roughly the distance from New York to Denver, except it's all underwater and carved deep into the ocean floor. The width of this underwater canyon averages 69 kilometers at its widest point, which might not sound enormous until you realize that's wider than Manhattan, stretched out 43 times over. This crescent-shaped depression represents one of the most distinctive geological features on our planet, visible even from satellite images as a dark blue gash cutting through the lighter blue of the surrounding ocean. The trench maintains its curved profile throughout its entire length, following the contours where two massive pieces of Earth's crust meet in an underwater collision that's been happening for millions of years. The deepest part of the Mariana Trench has a name that sounds like something from an adventure novel: Challenger Deep. This is named after the HMS Challenger 2, the British research vessel that first measured its incredible depth back in 1951. The Challenger Deep sits at the southern end of the trench, and here's where things get mind-bending. It plunges down to approximately 10,984 meters below sea level, give or take 25 meters, depending on which measurement you trust. The precision of measuring something nearly 7 miles underwater is incredibly difficult, which is why different expeditions have recorded slightly different depths over the years. The most recent measurements using advanced sonar technology suggest the deepest point reaches 10,935 meters, but the exact figure continues to be refined as our technology improves. To put this depth into perspective, imagine taking Mount Everest, the tallest mountain on Earth at 848 meters, and dropping it straight down into Challenger Deep. The peak would still sit more than 2 kilometers underwater, with over a mile of ocean still above the world's tallest mountain. It's like nature decided that going really high wasn't impressive enough, so it went ahead and created something that goes impossibly deep instead. The water pressure at this depth is more than 0 times greater than at sea level, equivalent to having about 50 jumbo jets pressing down on every square meter. The Mariana Trench's location isn't random. It sits right where two massive pieces of Earth's crust meet in what geologists call a subduction zone. We're talking about the Pacific Plate and the smaller Philippine Sea Plate, and they're locked in an incredibly slow-motion geological wrestling match that's been going on for millions of years. The Pacific Plate, which is older, cooler, and denser, gets shoved underneath the Philippine Sea Plate in a process scientists call subduction. Think of it like sliding one piece of paper under another, except these pieces of paper are chunks of ocean floor, dozens of kilometers thick, and moving at about the same rate your fingernails grow. This collision happens so slowly that you'd never feel it in a human lifetime. But over geological timescales, it's one of the most powerful forces shaping our planet. The Pacific Plate carries some of the oldest oceanic crust on Earth as it dives into the trench. We're talking about seafloor that's up to 170 million years old, formed when dinosaurs were just hitting their stride in the Middle Jurassic period. As this ancient crust descends into the Earth's mantle, it gets recycled back into the planet's interior, completing a cycle that has been going on since the earliest days of plate tectonics. The angle of this descent creates the steep walls of the trench, with the deepest parts formed where the descending plate bends most sharply as it begins its journey into the Earth's interior. Here's something that might surprise you about the Mariana Trench's neighborhood. It's part of a much larger system called the Izu-Bonin-Mariana Subduction Zone. This is part of a geological family that includes other deep-sea trenches stretching across the western Pacific. The whole system forms a boundary between tectonic plates that runs for thousands of kilometers, making the Mariana Trench just one member of an exclusive club of Earth's deepest places. This subduction system is responsible for some of the most dramatic underwater topography on our planet, creating not just the Mariana Trench, but also a series of underwater mountains, volcanic islands, and smaller trenches that dot the western Pacific. The system is incredibly active, geologically speaking, generating earthquakes, volcanic eruptions, and the constant recycling of oceanic crust. What makes the Mariana section special is that it represents the deepest point in this entire system, the place where the geometry of the plate collision and the age of the descending crust combine to create maximum depth. The surrounding trenches, like the Japan Trench and the Philippines Trench, are also incredibly deep, but none quite match the extreme depths found in the Mariana system. This entire network of trenches forms part of the Pacific Ring of Fire, that famous circle of seismic and volcanic activity that surrounds the Pacific Ocean. The coordinates of Challenger Deep, if you're the type who likes to look things up on maps, are approximately 1122.4 N 142.35.5 E. Now, those numbers might seem meaningless, but they pinpoint one of the most remote and extreme locations accessible on our planet. You're more likely to have cell phone service in some parts of Antarctica than you are to have any kind of communication with the outside world when you're floating directly above this spot. These coordinates place Challenger Deep in what's essentially the middle of nowhere in terms of human civilization, thousands of miles from major population centers and hundreds of miles from the nearest significant land masses. The remoteness of this location has made it one of the least explored places on Earth, visited by fewer people than have walked on the moon. The coordinates also place it in the tropics, which means the surface waters above are warm and teeming with life, creating a stark contrast to the cold, dark depths below. Interestingly, these coordinates have been refined over the decades as GPS technology has improved, and different expeditions have sometimes recorded slightly different positions for the deepest point, reflecting both the challenges of precise navigation at sea and the fact that the deepest point isn't a single spot, but rather a small area of extremely deep sea floor. The precision required to navigate to this exact location in the vast Pacific Ocean is a testament to modern technology. Without GPS satellites, finding this needle in an oceanic haystack would be nearly impossible. Speaking of remote locations, the nearest land to Challenger Deep is Face Island, one of the outer islands of Yap, sitting 287 kilometers to the southwest. Guam, which is much larger and more well-known, lies 304 kilometers to the northeast. To put this isolation in perspective, you could fit the entire state of Rhode Island in the empty ocean space between Challenger Deep and the nearest significant landmass, with room to spare. Face Island itself is tiny, just 2.8 square kilometers of coral and palm trees rising barely above sea level, home to fewer than 300 people who live a traditional Pacific Island lifestyle largely unchanged for generations. The contrast between this small tropical paradise and the abyssal depths of Challenger Deep just a few hundred kilometers away is one of the most dramatic geographical contrasts on our planet. Guam, while much larger and more developed, is still a relatively small island in the vast Pacific, serving as an important military and commercial hub for the region, but still feeling incredibly isolated when you're floating above the deepest part of the ocean. The distance to any major continental landmass is even more staggering. You'd have to travel over 0 kilometers to reach the Philippines, Japan, or Australia. This isolation has helped preserve the pristine nature of the deep sea environment around the trench, as human impacts have been minimal compared to coastal areas near major population centers. The remoteness also means that any research expedition to the trench requires careful planning and substantial resources, as rescue or resupply would take days or weeks to arrive in case of emergency. The Pacific Ring of Fire, that infamous circle of volcanoes and earthquake activity that surrounds the Pacific Ocean, includes the Mariana Trench as one of its most dramatic features. The Ring of Fire gets its name from all the volcanic activity, and the Mariana Trench sits right in the middle of this geological hot zone. It's like living in the most seismically active neighborhood on Earth, except your neighborhood is 7 miles underwater. The Ring of Fire is responsible for about 90% of the world's earthquakes and contains 75% of the world's active volcanoes, making it the most geologically active region on our planet. The Mariana Trench represents the deepest point in this ring of geological activity, where the forces that drive earthquakes and volcanoes are at their most extreme. The subduction process that created the trench continues to generate seismic activity, with deep earthquakes occurring regularly as the Pacific Plate grinds its way beneath the Philippine Sea Plate. These earthquakes can be felt hundreds of kilometers away and sometimes generate tsunamis that affect the entire Pacific Basin. The volcanic activity associated with this subduction zone has created the Mariana Islands themselves, along with numerous underwater volcanoes and hydrothermal vents that dot the seafloor around the trench. Some of these underwater volcanoes are active today, spewing lava and superheated water into the deep ocean, creating unique ecosystems that thrive in conditions that would be instantly lethal to most life on Earth. The Ring of Fire designation reminds us that the Mariana Trench is part of a dynamic, ever-changing system that continues to shape our planet today. The formation of the Mariana Trench is directly responsible for creating the Mariana Islands themselves, in what amounts to one of Earth's most impressive geological recycling programs. As the Pacific Plate gets forced down into the Earth's mantle, it carries water trapped in its rocks and minerals. When that water gets released under the extreme heat and pressure deep underground, it causes the rock above to melt and form magma. That magma eventually finds its way to the surface, creating the volcanic islands we see today. It's like the Earth's own recycling program, except instead of making new bottles, it's making new islands. The process works because the descending oceanic plate contains water locked in its crystal structure, and as the plate descends and heats up, this water is released and rises into the overlying mantle rock. Water lowers the melting point of rock, so the addition of this released water causes the mantle to partially melt, creating magma that's less dense than the surrounding solid rock. This magma rises toward the surface, sometimes erupting underwater to build seamounts and volcanic ridges, and sometimes breaking through the ocean surface to create islands. The Mariana Islands are the surface expression of this deep earth process, representing just the tips of massive volcanic mountains that rise from the ocean floor. The largest of these islands, Guam, rises over 0 meters from the seafloor to its highest point, making it part of a mountain range that, if measured from base to peak, rivals some of the tallest mountains on the continents. This island-building process continues today, with active volcanism still occurring in the region, slowly adding new land to the existing islands and potentially creating new ones over geological time. The age of the oceanic crust that's diving down into the Mariana Trench is absolutely mind-boggling. We're talking about some of the oldest oceanic crust on Earth, up to 170 million years old. To put that in perspective, this piece of ocean floor was forming when dinosaurs were just hitting their stride in the Middle Jurassic period. The rocks diving into this trench are older than the Atlantic Ocean itself, which didn't even start forming until about 130 million years ago. This ancient oceanic crust formed at mid-ocean ridges that no longer exist, created when the continents were arranged very differently than they are today. At that time, the supercontinent Pangaea was just beginning to break apart, and the Pacific Ocean was much smaller than it is today. The crust now descending into the Mariana Trench has been slowly moving across the Pacific for all these millions of years, covering thousands of kilometers at the rate of a few centimeters per year. During its long journey, this oceanic crust has accumulated sediments, been altered by seawater, and cooled from its original molten state into the dense, cold rock that now makes it heavy enough to sink back into the mantle. The extreme age of this crust is one reason why the Mariana Trench is so deep. Older oceanic crust is colder and denser than younger crust, so it sinks more readily into the underlying mantle. This creates steeper subduction angles and deeper trenches compared to areas where younger, more buoyant oceanic crust is being subducted. The recycling of this ancient crust back into the mantle completes a cycle that has been operating for billions of years, constantly renewing the ocean floor and helping to regulate the Earth's internal heat and chemical composition. The shape of the trench isn't uniform throughout its length. It's actually made up of 3 distinct basins that scientists have creatively named the Western, Central, and Eastern basins. Each basin has its own personality, with slightly different depths and characteristics that reflect the complex geometry of the subduction process. The Eastern Basin currently holds the record for the deepest measured point, though the differences between the 3 are relatively small when you're talking about depths that boggle the human mind. These basins are separated by underwater ridges and mounds that rise several hundred meters above the deepest parts, creating a landscape that looks somewhat like a series of connected swimming pools when viewed from above with sonar. The Western Basin, where the famous Trieste dive took place in 1960, reaches depths of over 900 meters and is characterized by relatively flat, sediment-covered floors. The Central Basin is slightly shallower, but features some of the most interesting geological formations, including evidence of underwater landslides and complex current patterns that have carved unusual features into the seafloor. The Eastern Basin, the current record holder for depth, is the narrowest of the 3, but appears to have the steepest walls and the most dramatic topography. Each basin represents a slightly different phase or aspect of the subduction process, with variations in the angle of the descending plate, the amount of sediment being carried down, and the local stress patterns in the overlying crust. These variations create the complex 3-dimensional structure of the trench, making it not just a simple V-shaped cut in the ocean floor, but a sophisticated landscape of peaks, valleys, and basins that continues to evolve as the subduction process continues. The deepest land-based location accessible to humans is the Krubra Cave in Georgia, which extends to 197 meters below the surface. That would put you less than 20% of the way down to Challenger Deep. The deepest mine shaft in the world, the Mumponeng Gold Mine in South Africa, reaches 40 meters below the surface. Impressive for a human-made hole, but still less than 40% of the way to the bottom of the trench. Even if you combined the depth of the deepest mine with the height of the tallest building humans have ever constructed, the Burj Khalifa, at 828 meters, you'd still be more than 6 kilometers short of reaching Challenger. The deepest humans have ever drilled into the Earth is the Kola super deep borehole in Russia, which reached 262 meters below the surface. That's actually deeper than Challenger Deep, but it's a narrow hole, only 23 centimeters wide, drilled through solid rock over the course of 21. Here's where things get absolutely mind-bending. The precise measurement of Challenger Deep has been a moving target for decades, and it's not because scientists can't agree on how to use a ruler. The challenge of measuring something nearly 7 miles underwater is like trying to measure the height of a skyscraper from space while riding a roller coaster during an earthquake. The most recent high-precision measurements put Challenger Deep at 935 meters below sea level, give or take 6 meters. That margin of error might seem small, but when you're dealing with the deepest point on Earth, even those 6 meters represent years of scientific debate and technological advancement. Different expeditions have recorded measurements ranging from 902 meters to 984 meters, and the variations reflect the incredible difficulty of measuring depth in an environment where water pressure can crush a submarine like a tin can, and sound waves behave differently than they do at the surface. The seafloor at this depth isn't perfectly flat either. It undulates with ridges and depressions that can vary by tens of meters over short distances. Modern multi-beam sonar systems can map these variations with unprecedented detail, but they still face the challenge of accounting for water temperature, salinity, and pressure variations that affect how sound travels through the water column. The most accurate measurements now combine direct pressure readings from submersibles with sophisticated sonar mapping, creating a three-dimensional picture of the deepest seafloor that's more detailed than maps of some terrestrial mountain ranges. The comparison everyone makes, and for good reason, is dropping Mount Everest into Challenger Deep like the world's most extreme swimming pool. Mount Everest stands 848 meters above sea level, which means if you could somehow transport it to the bottom of Challenger Deep, its peak would still be sitting 87 meters underwater. That's over 1.25 miles of ocean above the world's tallest mountain. But here's what really puts this into perspective. The vertical relief from the bottom of Challenger Deep to the top of Mount Everest would be 783 meters. That's nearly 20 kilometers of vertical distance, or about 12.3 miles. If you could somehow stack them together, this combined height would be more than twice the cruising altitude of commercial airliners. The comparison gets even more striking when you consider that Mount Everest took millions of years to form through the collision of tectonic plates, pushing land upward, while Challenger Deep was carved by those same tectonic forces, pulling the seafloor downward. They're essentially mirror images of the same geological processes, one reaching toward space, the other plunging toward the center of the Earth. The atmospheric pressure at the top of Everest is about 1/3 of sea level pressure, while the water pressure at the bottom of Challenger Deep is over 10 times sea level pressure. A human being would die in minutes at either location without protection, but for completely opposite reasons: too little pressure versus too much. Let's talk about stacking Empire State Buildings, because sometimes you need a really tall, human-made structure to wrap your head around these depths. The Empire State Building, including its antenna, stands 443 meters tall. To reach the bottom of Challenger Deep, you'd need to stack about 25 Empire State Buildings on top of each other. Picture that for a moment, 25 of those iconic Art Deco skyscrapers balanced end to end, stretching down through increasingly dark water until the bottom one sits in the abyssal depths where no sunlight has ever penetrated. Each building in this impossible stack would experience dramatically different conditions. The top one would be in warm, sunlit tropical waters, teeming with life, while the bottom building would sit in near-freezing water under crushing pressure in a world of perpetual darkness. By the time you got to the 5th building down, you'd be deeper than most submarines can safely travel. By the 10th building, you'd be in the Hadal Zone, a realm so extreme that it has its own specialized life forms. The bottom 15 buildings would exist in conditions more alien than the surface of Mars. At least Mars has an atmosphere you could theoretically breathe with the right equipment. The pressure at the bottom of our Empire State Building stack would be equivalent to having 50 of those same buildings sitting on top of every square meter of surface. It's a comparison that really drives home not just the depth, but the incredible hostility of the environment at the bottom of our oceans. Commercial airliners typically cruise at altitudes between 9, 0, and 12, 0 meters above sea level, heights that put them in the stratosphere where the air is thin and the views are spectacular. Here's the kicker. Challenger Deep is deeper below sea level than most airplanes fly above it. While your typical Boeing 747 cruises at about 11, 0 meters altitude, the bottom of Challenger Deep sits at 10, 935 meters below the surface. This means that if you could somehow flip the ocean upside down, the deepest point would be flying at nearly the same altitude as your vacation flight to Hawaii. The comparison becomes even more surreal when you consider the environments. At 11, 0 meters altitude, the air temperature is around minus 55 degrees Celsius. The air pressure is so low that your blood would literally boil without a pressurized cabin, and you're above 90% of the Earth's atmosphere. At 10, 935 meters below sea level, the water temperature hovers just above freezing. The pressure is over 100 times greater than at sea level, and you're beneath 100% of the world's ocean. Both environments are utterly hostile to human life, but for completely opposite reasons. A human being would survive about the same amount of time at either location without protection, which is to say, not very long at all. The irony is that we've built machines that can routinely carry hundreds of people to the altitude equivalent of Challenger Deep's depth, but only a handful of specially designed vessels have ever reached the bottom of the trench, and they've carried just a few dozen people total throughout all of human history. When we start comparing Challenger Deep to other deep places in the ocean, its supremacy becomes even more impressive. The second deepest point in our oceans is the Horizon Deep in the Tonga Trench, which reaches about 10,882 meters. That makes Challenger Deep roughly 50 meters deeper than its nearest competitor, and in the world of deep-sea records, 50 meters is like winning the Olympics by a full second. The Peru-Chile Trench, which runs along the western coast of South America, reaches maximum depths of about 65 meters, impressive by any standard, but still nearly 3 kilometers shallower than Challenger Deep. The Japan Trench, site of the devastating 2011 earthquake and tsunami, plunges to about 412 meters at its deepest point. Even the Puerto Rico Trench, the deepest point in the Atlantic Ocean at 376 meters, would seem like a shallow valley compared to the Mariana Trench. These comparisons highlight just how exceptional the Mariana Trench really is. It's not just slightly deeper than other ocean trenches, it's in a completely different league. The geological conditions that created Challenger Deep, the age and density of the subducting Pacific Plate, the angle of subduction, and the local stress patterns in the Earth's crust, combined to create something truly unique. If Challenger Deep were a building, every other deep ocean trench would be looking up at it from several floors below. Here's a visual analogy that might help you grasp the scale. Imagine if the entire depth of Challenger Deep was compressed into the height of a typical 2-story house, about 6 meters tall. On this scale, the deepest a human being has ever gone without breathing equipment, about 330 meters in a free dive, would be represented by just 18 centimeters, or about 7 inches. That's roughly the thickness of a large book. The deepest point a human has reached with scuba gear, around 10 meters using specialized gas mixtures, would scale to about 55 centimeters, or less than 2 feet. The average depth of the world's oceans, about 688 meters, would come up to just over 2 meters, not even reaching the second floor of our imaginary house. Nuclear submarines, which can dive deeper than any other military vessels, typically operate at depths of around 500 meters, which on our scale would be ankle deep. Even the most advanced deep-sea research submarines can only reach depths of about 0 meters, which would put them at roughly waist-high in our 2-story house analogy. This really drives home how the vast majority of our planet's deepest places remain completely inaccessible to direct human exploration. We've literally explored more of the surface of the moon than we have of the deepest parts of our own oceans. The pressure at the bottom of Challenger Deep is so extreme that it defies easy comparison. But here's one that might stick with you. It's equivalent to having about 50 jumbo jets sitting on every square meter of surface. Another way to think about it is that the water pressure at Challenger Deep is roughly the same as what you'd experience if you were somehow transported to a depth of 10 kilometers inside a solid rock, except instead of being crushed instantly, you're in a submarine designed to keep that pressure out. The technical measurement is about 186 bars of pressure, or roughly 171 times the air pressure you're experiencing right now as you listen to this. To put that in perspective, a car tire is typically inflated to about 2 bars of pressure. At Challenger Deep, the pressure is more than 500 times greater than what's in your tires. Deep-sea diving bells that work in the North Sea oil fields, operating at depths of 200-300 meters, deal with pressures of about 20-30 bars, child's play compared to the crushing forces at the bottom of the trench. The human body, which is mostly water, would actually withstand this pressure surprisingly well if it weren't for the gas-filled spaces like our lungs, sinuses, and the air in our digestive tract. Those would be compressed to virtually nothing instantly. This is why the few vehicles that have reached Challenger Deep require pressure hulls made of specially designed titanium or steel spheres with walls several inches thick, and even then, the margin for error is razor thin. If you were to take a road trip from sea level down to Challenger Deep, and somehow that road descended at a reasonable 6% grade like you might find on a mountain highway, you'd need to drive for about 183 kilometers. That's roughly the distance from New York City to Philadelphia, just to reach the bottom. Along the way, you'd pass through distinct zones of the ocean, each with its own unique characteristics. The first 200 meters would be the sunlight zone, where you might see tropical fish and coral reefs giving way to darker waters. Between 201.0 meters, you'd be in the twilight zone, where the last traces of sunlight disappear and bioluminescent creatures begin to dominate. From 10 to 40 meters, you'd be driving through the midnight zone, where the water temperature drops to just above freezing and the pressure becomes crushing. The final stretch, from 40 meters all the way down to the bottom, would take you through the abyssal and hadal zones, realms so alien that they might as well be on another planet. Your 183-kilometer road trip would take you through environments more varied and extreme than a journey from the Amazon rainforest to the Antarctic ice sheets. By the time you reach the bottom, you'd have descended through water that represents 99% of the livable space on our planet, yet remains less explored than the surface of Mars. Here's something that'll really mess with your sense of scale. If Challenger Deep were somehow drained of water and you were standing at the bottom, looking up, the surface of the ocean would appear to curve away from you due to the curvature of the Earth. At that depth, you'd be so far below the surface that the horizon, if you could somehow see it through 11 kilometers of empty space, would actually be below your eye level. This is the same optical effect you'd experience if you were standing on top of a mountain that was 11 kilometers tall, except you'd be in a hole instead of on a peak. The walls of this imaginary drain trench would rise around you at angles steeper than most cliff faces, creating a V-shaped canyon that would make the Grand Canyon look like a small creek bed. If the sun were directly overhead, it would appear as a tiny bright dot almost straight above you, and the sky would look like a small circle of blue surrounded by the dark walls of the trench. Sound would behave strangely in this deep canyon. A shout from the bottom would take several seconds to echo back from the surface, and the acoustics would create strange reverberations off the steep walls. Of course, this scenario is purely imaginary, since the water pressure is what carved the trench in the first place, but it helps illustrate just how profound this depth really island. You'd literally be standing in a hole deep enough that you could see the curvature of our planet from the bottom. The volume of water sitting above Challenger Deep is staggering in its own right. If you could somehow extract just the column of water directly above the deepest point, imagine a cylinder 11 kilometers tall with a diameter of just 1 kilometer, you'd have roughly 8.6 billion liters of water. That's enough water to supply a city of 100 people for about 6 months. But here's the thing that really puts the scale in perspective. That's just one tiny column in an ocean that covers more than 70% of our planet's surface. The Pacific Ocean alone contains about 710 million cubic kilometers of water, which means our little column represents about 0.000001% of just one ocean. This really drives home how vast our oceans are. Challenger Deep, for all its record-breaking depth, is just one point in an aquatic realm so large that it defies human comprehension. The deepest point on Earth sits beneath a volume of water so immense that all the continents could fit inside it with room to spare. And yet, despite this vastness, humans have explored less than 5% of the ocean, and most of that exploration has been limited to the upper layers, where sunlight can still penetrate. When we compare Challenger Deep to other extreme places on Earth, the scale becomes even more remarkable. The deepest land-based location accessible to humans is the Krubera Cave in Georgia, which extends 197 meters below the surface. That would put you less than 20% of the way down to Challenger Deep. The deepest mine shaft in the world, the Mponeng Gold Mine in South Africa, reaches 40 meters below the surface. Impressive for a human-made hole, but still less than 40% of the way to the bottom of the trench. Even if you combine the depth of the deepest mine with the height of the tallest building humans have ever constructed, the Burj Khalifa, at 828 meters, you'd still be more than 6 kilometers short of reaching Challenger Deep. The deepest humans have ever drilled into the Earth is the Kola Super Deep borehole in Russia, which reached 262 meters below the surface. That's actually deeper than Challenger Deep, but it's a narrow hole only 23 centimeters wide drilled through solid rock over the course of 20 years, hardly comparable to the vast underwater canyon of the Mariana Trench. The borehole project was eventually abandoned because the temperatures at that depth reached 180 degrees Celsius, far hotter than the near-freezing temperatures found at the bottom of Challenger Deep. This comparison highlights one of the remarkable things about the deep ocean. It's one of the few places on Earth where you can reach extreme depths while still finding conditions that, while hostile, are not immediately lethal to properly designed equipment. The speed of sound in water changes with depth, and this creates some fascinating effects when we think about the scale of Challenger Deep. At the surface, sound travels through seawater at about 500 meters per second. At the bottom of Challenger Deep, where the water is colder and under immense pressure, sound travels slightly faster, about 550 meters per second. This means that if you could somehow make a noise at the surface directly above Challenger Deep, it would take about 7 seconds for that sound to reach the bottom of the trench. That might not seem like much, but it's long enough that you could clap your hands, count 1 Mississippi, 2 Mississippi, all the way to 7, and then the sound would finally reach the deepest point on Earth. This time, delay has practical implications for deep-sea exploration. When submarines at the bottom of the trench communicate with ships on the surface using acoustic signals, there's always this 7-second delay in each direction, making real-time conversation impossible. It's like having a phone conversation with someone on another planet, except the delay is caused by the sheer depth of our own oceans. This acoustic property also means that the deepest parts of the ocean are naturally isolated from the sounds of the surface world. The noise of ships, storms, and human activity takes time to penetrate to these depths, creating acoustic environments that have remained relatively unchanged for millions of years. Here's a comparison that really brings the depth into focus. If you could somehow take an elevator from the surface down to Challenger Deep, and that elevator moved at the same speed as a typical city elevator, about 2 meters per second, it would take you about 91 minutes to reach the bottom. That's longer than most movies, longer than a typical soccer match, including overtime, and long enough to listen to about 25 songs on your playlist. During that hour-and-a-half ride, you'd pass through every major zone of the ocean, watching the water outside your imaginary elevator car grow progressively darker and more alien. For the first 10 minutes of your descent, you might still see some sunlight filtering down from above. By the 15-minute mark, you'd be in permanent darkness. After half an hour, you'd be deeper than any recreational scuba diver has ever gone. At the 45-minute mark, you'd be deeper than most military submarines can safely travel. And for the final 45 minutes of your journey, you'd be descending through realms that fewer humans have visited than have walked on the moon. When you finally reach the bottom after that 91-minute journey, you'd be in one of the most remote and extreme environments on our planet, surrounded by crushing pressure and eternal darkness, yet also in one of the most scientifically fascinating places on Earth. The comparison between Challenger Deep and outer space is more apt than you might think, and it really puts the achievement of reaching the bottom into perspective. The International Space Station orbits about 400 kilometers above Earth's surface. That's roughly 37 times higher than Challenger Deep is deep. But here's the thing, we've sent thousands of people into space, while fewer than 30 people have ever been to the bottom of Challenger Deep. It's actually easier to send someone to the International Space Station than it is to send them to the deepest point in our oceans. The space station is supplied regularly by cargo ships and crew rotation vehicles, while each trip to Challenger Deep represents a major expedition requiring specialized equipment and years of planning. An astronaut on the space station can look out the window and see the entire Pacific Ocean, including the tiny area above Challenger Deep, yet that astronaut is closer to home than the handful of people who have made the journey to the bottom of the trench. This comparison really highlights how much more challenging it is to explore the deep ocean than it is to explore near-Earth space. The pressure, darkness, and corrosive nature of seawater create engineering challenges that are in many ways more difficult to overcome than the vacuum and radiation of space. The pressure at the bottom of Challenger Deep is so intense that if you could somehow transport a styrofoam coffee cup down there, it would shrink to the size of a thimble in seconds. We're talking about 1/86 times the atmospheric pressure you're experiencing right now. To put this in perspective, imagine having the weight of about 50 jumbo jets pressing down on every square meter of your body. That's roughly 750 pounds per square inch, or about 1/86 bar in scientific terms. Your car tires are inflated to maybe 2.2 bar. At Challenger Deep, you're dealing with pressure that's nearly 500 times greater than what keeps your tires properly inflated. This crushing force is so extreme that it would instantly compress any air-filled space to virtually nothing. The human body, being mostly water, could theoretically survive this pressure if it weren't for those pesky, air-filled cavities, like our lungs, sinuses, and digestive tract. Those would be squeezed down to practically nothing faster than you could blink. This is why the submarines that visit these depths need pressure hulls made of specially designed titanium spheres with walls several inches thick. Even then, the engineering tolerances are so tight that a tiny flaw in the metal could result in catastrophic implosion. The pressure is so immense that it literally changes the fundamental properties of water itself. At these depths, water becomes slightly more dense and behaves differently than the water you drink from your tap. Now, here's something you might find surprising. The temperature at the bottom of Challenger Deep hovers between 1 and 4 degrees Celsius, which is just above freezing. You'd expect it to be warmer down there, right? After all, we're getting closer to the Earth's hot interior. But the thing is, we're still nowhere near close enough for that internal heat to matter much. The water at these depths maintains this near-freezing temperature year-round, creating one of the most stable thermal environments on our planet. Compare that to the surface waters above, which in the tropical Pacific can reach 30 degrees Celsius or more. That's a temperature difference of nearly 30 degrees between the surface and the bottom. This temperature gradient creates fascinating dynamics in the water column. Warm water is less dense than cold water, so the surface waters tend to stay on top, while the cold, dense water sinks to the bottom. This creates what oceanographers call thermal stratification, where distinct layers of water at different temperatures stack on top of each other like a liquid layer cake. The cold temperatures at depth also affect how gases dissolve in seawater. Cold water can hold more dissolved oxygen than warm water, which is crucial for the life forms that manage to survive down there. Interestingly, these frigid temperatures also mean that organic matter that sinks from the surface decomposes extremely slowly. A piece of wood or a dead fish that reaches the bottom of Challenger Deep might take decades or even centuries to fully decompose, essentially creating a natural time capsule of organic material. Moving on to something that might fascinate you, the water at the bottom of Challenger Deep isn't quite the same as the water at the surface. And I'm not just talking about temperature. The immense pressure actually changes the molecular structure and behavior of water itself. Under normal conditions, water molecules are constantly moving and bouncing around. But under the crushing pressure of the deep ocean, these molecules are forced much closer together. This makes the water about 5% more dense than it is at the surface, which might not sound like much, but it has profound effects on everything from how sound travels to how gases dissolve. The pressure also affects the freezing point of water. Under these conditions, pure water wouldn't freeze until the temperature dropped to about -2.5 degrees Celsius, compared to 0 degrees at the surface. But here's where it gets really interesting. The water down there also contains different concentrations of dissolved minerals and gases compared to surface water. The high pressure allows the water to hold much more dissolved carbon dioxide, creating slightly more acidic conditions. This increased acidity, combined with the pressure, means that calcium carbonate, the stuff that makes up seashells and coral skeletons, dissolves much more readily. This is why you won't find any shelled creatures living at these depths. Their shells would literally dissolve in the acidic, high-pressure environment. The water chemistry is so different that scientists sometimes refer to the deep ocean as a completely different liquid environment, even though it's technically the same H2O we're familiar with at the surface. Believe it or not, one of the most striking features of life at Challenger Deep is the complete and utter absence of sunlight. We're not talking about dim light or filtered light. We're talking about absolute total darkness that has persisted for millions of years. Sunlight can only penetrate about 0 meters into the ocean under the best conditions, and even that's being generous. By the time you reach 0 meters deep, you're in complete darkness, and Challenger Deep is more than 5 times deeper than that. This means that the bottom of the trench exists in a realm of perpetual night that makes the darkest cave on land seem bright by comparison. No photosynthesis can occur at these depths, which fundamentally changes the entire ecosystem. Instead of plants forming the base of the food web like they do on land and in shallow water, the deep ocean relies on what scientists call marine snow, a constant gentle rain of organic matter that drifts down from the surface layers where photosynthesis does occur. This marine snow consists of dead plankton, fecal pellets, and other organic debris that slowly sinks through the water column, providing the only source of nutrition for deep sea life. The journey from surface to seafloor can take weeks or months, and much of the organic matter gets consumed by creatures living in the water column above, so only a small fraction actually reaches the bottom. This makes the deep ocean floor one of the most food-scarce environments on Earth, where creatures must be incredibly efficient at finding and utilizing every scrap of nutrition that drifts down from above. Here's something that'll really get your attention. Sound behaves completely differently in the extreme environment of Challenger Deep compared to what you're used to on land. The combination of crushing pressure, near-freezing temperatures, and the dense water creates acoustic conditions that are unlike anywhere else on Earth. Sound travels about 4 times faster through water than through air under normal conditions, but at the bottom of Challenger Deep, it travels even faster, roughly 550 meters per second, compared to 343 meters per second in air at sea level. This means that a sound made at the bottom of the trench would reach you much more quickly than the same sound made in air. But here's the kicker. There's very little down there to make sound in the first place. The deep ocean is one of the quietest environments on our planet, with background noise levels that would be the envy of any recording studio. The main sounds come from the occasional earthquake, the settling of sediments, and the rare movements of deep-sea creatures. But when sounds do occur, they can travel for enormous distances. The deep ocean acts like a giant acoustic waveguide, allowing low-frequency sounds to propagate for thousands of kilometers with very little attenuation. This is how whales can communicate across entire ocean basins, and it's also how scientists can detect underwater earthquakes and volcanic eruptions from thousands of miles away. The acoustic properties of deep water are so reliable that during the Cold War, both the United States and Soviet Union used underwater sound detection networks to track submarines across entire oceans. Next up, let's talk about something truly mind-bending. The chemical environment at Challenger Deep is like nowhere else on our planet. The extreme pressure fundamentally alters chemical reactions and the behavior of dissolved substances. Under normal surface conditions, many chemical reactions proceed at predictable rates, but under the crushing pressure of the deep ocean, these same reactions can speed up, slow down, or even reverse direction entirely. The high pressure also allows water to dissolve gases and minerals that would normally remain separate under surface conditions. For example, the water at Challenger Deep contains much higher concentrations of dissolved gases, like carbon dioxide, nitrogen, and even hydrogen sulfide in some areas. These dissolved gases create unique chemical conditions that can support specialized forms of life that literally couldn't exist anywhere else. The pressure also affects the pH of the water, making it more acidic than surface water. This increased acidity, combined with the high concentrations of dissolved minerals, creates a corrosive environment that can eat away at metal and rock over time. Scientists have found that equipment left at these depths for extended periods shows significant corrosion damage, with metal components literally dissolving into the surrounding water. The chemical composition of the water itself tells a story of the trench's geological activity. Elevated levels of certain minerals indicate ongoing interactions between seawater and the Earth's mantle, providing clues about the deep geological processes that continue to shape our planet. Speaking of chemical gradients, here's something you might not expect. The water column above Challenger Deep is like a layered cocktail, with each layer having its own distinct chemical signature. As you descend from the surface to the bottom, you pass through distinct zones where the concentration of dissolved oxygen, nutrients, and other chemicals changes dramatically. Near the surface, photosynthesis by marine plants and algae keeps oxygen levels high, but as you descend, this oxygen gets consumed by bacteria and other organisms, breaking down organic matter. By the time you reach about 0 meters depth, you enter what oceanographers call the oxygen minimum zone, where dissolved oxygen levels drop to nearly zero. This creates a natural barrier that many marine organisms simply cannot cross. Below this zone, oxygen levels increase slightly again, but they never reach the high concentrations found near the surface. At the bottom of Challenger Deep, dissolved oxygen levels are just high enough to support the specialized life forms that live there, but they're still only a fraction of surface levels. The nutrient concentrations also change with depth, creating distinct layers where different types of microorganisms thrive. These chemical gradients act like invisible boundaries in the water column, creating distinct ecological zones that are as different from each other as deserts are from rainforests on land. Understanding these chemical layers is crucial for scientists studying deep-sea life, because each layer presents unique challenges and opportunities for the organisms that live there. Let me tell you something that'll absolutely amaze you. The pressure at Challenger Deep is so extreme that it can actually squeeze gas bubbles out of existence. If you could somehow bring a balloon filled with air down to these depths, it wouldn't just shrink. The air inside would be compressed so much that it would eventually dissolve completely into the surrounding water. This phenomenon, called pressure dissolution, occurs because gases become much more soluble in liquids under high pressure. It's the same principle behind carbonated beverages, where carbon dioxide is dissolved into water under pressure, but taken to an extreme that defies everyday experience. The pressure is so intense that it can force gas molecules to behave in ways that seem to violate our normal understanding of physics. For instance, under these conditions, gases can actually become denser than some liquids, creating bizarre situations where what we normally think of as light gases become heavy and sink rather than rise. This extreme pressure also affects how gases are stored in the seafloor sediments. Methane and other gases that would normally bubble up to the surface in shallow water can be trapped and concentrated in deep-sea sediments under the immense pressure, creating deposits of gas hydrates, essentially frozen gas trapped in ice-like crystals that only remain stable under these extreme conditions. These gas hydrate deposits represent one of the largest reservoirs of carbon on our planet, locked away under pressure in the deepest parts of our oceans. Now, here's something that really drives home the alien nature of this environment. The pressure at Challenger Deep is so great that it affects the fundamental behavior of materials in ways that can seem almost magical. Metals that are normally rigid become more plastic and deformable. Plastics that are flexible at the surface become brittle and can shatter like glass. Even the walls of pressure vessels, made from the strongest materials known to science, must be designed with incredible precision to avoid catastrophic failure. The pressure hull of a deep-sea submersible is engineered down to the molecular level to distribute stress evenly and prevent the formation of microscopic cracks that could propagate into complete structural failure. The mathematics involved in designing these pressure vessels is so complex that it requires some of the most advanced computer modeling techniques available to engineering science. But here's what's truly remarkable. Despite this crushing environment that destroys most materials, life has found ways not just to survive, but to thrive. The organisms that live at these depths have evolved cellular structures and biochemical processes that actually require high pressure to function properly. Bring them to the surface, and they would die just as surely as a surface organism would be crushed at depth. They've essentially evolved to live in a high-pressure world with specialized proteins and cellular structures that only work properly under conditions that would be instantly fatal to surface life. Here's something that might blow your mind. The water at Challenger Deep is under so much pressure that its density is actually measurably different from surface water. While the difference is only about 5%, that's enough to create significant effects on anything that moves between different pressure zones. This density difference is one reason why water masses from different depths don't mix easily. The denser deep water tends to stay at the bottom while the lighter surface water remains on top. It's like trying to mix honey and water. The different densities create natural barriers to mixing. This density stratification is crucial for maintaining the distinct chemical and biological zones in the ocean. But it also means that pollutants or other substances that sink to the deep ocean tend to stay there for very long periods. The deep ocean acts like a vast storage reservoir, holding on to whatever falls into it for decades, centuries, or even millennia. This is both fascinating from a scientific perspective and concerning from an environmental one, because it means that deep-sea pollution can persist far longer than surface pollution. The pressure-induced density changes also affect how currents flow in the deep ocean. Deep water currents are driven primarily by density differences rather than wind or surface heating, creating a slow-moving but powerful circulation system that transports water masses around the globe over timescales of hundreds or thousands of years. Moving on to something truly extraordinary, the pressure at these depths is so extreme that it can actually change the shape of molecules themselves. Under normal conditions, many molecules have preferred three-dimensional shapes that determine how they interact with other molecules. But under the crushing pressure of the deep ocean, these molecular shapes can be distorted or compressed, fundamentally altering their chemical and biological properties. This is particularly important for biological molecules like proteins and DNA, which rely on their precise three-dimensional structures to function properly. Deep-sea organisms have evolved specialized versions of these molecules that maintain their proper shapes, even under extreme pressure, using what scientists call pressure-resistant or piezophilic adaptations. These adaptations are so specific to high-pressure environments that they represent entirely different evolutionary solutions to the same biological problems faced by surface organisms. In some cases, the pressure adaptations are so extreme that deep-sea organisms literally cannot survive in lower-pressure environments. Their specialized molecules fall apart or stop functioning when the pressure is reduced. This creates what biologists call obligate barophiles, organisms that absolutely require high pressure to live, making them some of the most environmentally specialized life forms on our planet. Believe it or not, the chemical environment at Challenger Deep includes concentrations of dissolved minerals that would be considered toxic in most surface environments. The combination of high pressure, low temperature, and the ancient age of deep-sea water allows it to accumulate dissolved substances over extremely long periods. Some deep-sea waters haven't been in contact with the atmosphere for over 10 years, giving them time to dissolve minerals from sediments and underwater rock formations. This creates water chemistry that's radically different from what we're familiar with at the surface. Heavy metals like lead, mercury, and cadmium can reach concentrations that would be dangerous to surface life, but deep-sea organisms have evolved mechanisms to either avoid these toxins or safely process them. The water also contains elevated levels of hydrogen sulfide in some areas, particularly near hydrothermal vents, creating conditions that would be immediately lethal to most surface life, but actually support thriving ecosystems of specialized bacteria and other organisms. These chemical conditions have remained relatively stable for geological timescales, allowing evolution to fine-tune organisms specifically for this unique environment. The result is a chemical ecosystem that operates by completely different rules than anything found in surface waters, with organisms that have biochemical pathways and metabolic processes unlike anything else on Earth. Here's something that'll really capture your imagination. The pressure gradient from the surface to Challenger Deep creates distinct pressure zones that act like invisible ecological barriers. Just as mountain ranges create different climate zones at different elevations, the ocean's pressure gradient creates different biological zones at different depths. Each zone has its own characteristic pressure range that supports specific types of organisms adapted to those conditions. The transition between these zones isn't gradual. There are often sharp boundaries where the biological communities change rapidly with relatively small changes in depth and pressure. These pressure barriers are so significant that they can prevent genetic mixing between populations of the same species living at different depths, leading to the evolution of distinct deep-sea species that are found nowhere else. Some organisms have evolved the ability to migrate vertically through these pressure zones, but they must do so slowly to avoid pressure-related injuries, and they often undergo significant physiological changes during their migrations. The most extreme pressure zone is the Hodl zone, which includes places like Challenger Deep, where the pressure exceeds 600 times surface pressure. This zone supports some of the most pressure-adapted life forms on Earth, organisms so specialized for high-pressure life that they represent evolutionary pinnacles of pressure adaptation. The Hodl zone is essentially Earth's final frontier for life, pushing the absolute limits of what biological systems can tolerate while still maintaining the complex chemistry necessary for life. Now let's talk about something that really puts the environmental extremes into perspective. The pressure at Challenger Deep is actually greater than the pressure found inside a nuclear reactor core. While nuclear reactors operate at pressures of about 150–160 bar, Challenger Deep experiences pressures of over 186 bar. This comparison really drives home just how extreme these conditions are. We're talking about pressures that exceed some of the most extreme human-engineered environments. The engineering challenges of building equipment that can function at these pressures are so severe that only a handful of vehicles in human history have ever successfully reached these depths and returned to the surface intact. Even more remarkably, The organisms that live at these depths do so without any of the elaborate pressure vessels and safety systems that human technology requires. They've solved the engineering problem of high-pressure survival through millions of years of evolution, developing biological solutions that are often more elegant and efficient than anything human engineering has achieved. The fact that complex life can not only survive, but thrive under pressures that challenge our most advanced technology is a testament to the incredible adaptability of life and the power of evolutionary processes to find solutions to seemingly impossible challenges. These organisms essentially live inside natural biological pressure suits that allow them to function normally in an environment that would instantly crush any unprotected surface organism, making them some of the most remarkable survivors on our planet. Now that we've explored the extreme physical conditions of the deep ocean, it's time to meet the incredible creatures that have found ways to thrive in this alien world. First up, there are single-celled organisms living at the bottom of the Mariana Trench that are bigger than a mango. I know, right? We're talking about creatures called xenophyophores, and they're basically the giants of the single-celled world. Picture this. Most single-celled organisms are microscopic, but these bad boys can grow up to 10 centimeters across. That's about 4 inches of pure single-celled weirdness. They look like spongy, alien blobs scattered across the seafloor, and they're so fragile that scientists have trouble studying them because they fall apart at the slightest touch. These creatures are essentially living proof that bigger isn't always better when it comes to cellular complexity. Instead of evolving into multicellular organisms like most life forms, xenophyophores decided to go the route of becoming massive single cells with incredibly complex internal structures. They build delicate shells, or tests, out of organic cement, mixed with whatever debris they can find on the seafloor, sand grains, bits of shell, even microscopic glass spheres from ancient marine organisms. What's really fascinating is that these creatures have been around for over 500 million years, making them some of the oldest life forms on our planet. They've survived multiple mass extinctions by perfecting the art of living slowly and efficiently in one of Earth's most stable environments. Scientists think they might play a crucial role in deep-sea ecosystems by providing structure and habitat for smaller organisms, essentially acting like underwater apartment buildings for microscopic life. Now, speaking of creatures that have mastered life in the deep, let me tell you about the supergiant amphipods, and trust me, these little guys are way cooler than their name suggests. Amphipods are basically the shrimp's weird cousins, and the ones living in the Mariana Trench have evolved some absolutely mind-blowing adaptations. The species Hirandelia gigas, discovered in the deepest parts of the trench, has figured out something that no other known organism on Earth has managed. They use aluminum to strengthen their exoskeletons. I know what you're thinking. Aluminum? Like the stuff in soda cans? Exactly. These tiny crustaceans, measuring just a few centimeters long, have somehow figured out how to extract aluminum from the seafloor sediments and incorporate it into their bodies to help them withstand the crushing pressure. It's like they're wearing natural aluminum armor, which is pretty incredible when you consider that aluminum is toxic to most life forms. But here's where it gets even more interesting. These amphipods are thriving in pressure. They've been found in massive swarms, sometimes thousands of individuals clustered together, feeding on whatever organic matter drifts down from the surface. Their bodies are completely transparent, which helps them blend into their environment, and they have oversized gills that help them extract oxygen from the oxygen-poor deep water. What really sets them apart is their reproduction strategy. Unlike their shallow water cousins, deep-sea amphipods can reproduce multiple times throughout their lives, which is crucial in an environment where finding a mate might be a once-in-a-lifetime opportunity. Moving on to something that'll make you rethink what you know about fish, let me introduce you to the Mariana snailfish, officially known as Pseudoleparus swirae. This little guy holds the record as the deepest living fish known to science, found at depths exceeding 0 meters below the surface. When you first see one, you might think it looks like a translucent tadpole that someone stretched out a bit too much. But don't let its simple appearance fool you. This fish is a masterpiece of evolutionary engineering. The snailfish has completely abandoned the traditional fish body plan that works so well in shallow water. It has no scales, no swim bladder, and no rigid bone structure. Instead, its skeleton is made of soft cartilage that can flex and bend under pressure. Its skin is so transparent you can see its internal organs, giving it an almost ghostly appearance as it glides through the water. But here's the really cool part. These fish have special proteins in their cells, called piezolites, that actually help them function better under pressure. While most proteins would be crushed or deformed by the intense pressure of the deep ocean, the snailfish's proteins are designed to work optimally in high-pressure environments. They feed primarily on tiny amphipods and other small crustaceans, using their large mouths to vacuum up prey from the seafloor. What's particularly remarkable is how they've adapted their entire lifestyle to the scarcity of food in the deep ocean. They move slowly and efficiently, conserving energy and making the most of every meal. The species was only discovered in 2017, and scientists named it after Herbert Swire, a crew member on the original HMS Challenger expedition that first explored these depths in the 1870s. Here's something that might surprise you. The deep ocean is absolutely teeming with microorganisms that not only survive in conditions that would kill most life on Earth, but actually require those extreme conditions to thrive. These are called extremophiles, and the ones living in the Mariana Trench represent some of the most specialized life forms on our planet. We're talking about bacteria and archaea that have evolved to live in crushing pressure, near freezing temperatures, complete darkness, and often in the presence of toxic chemicals that would be lethal to surface life. Some of these microorganisms live in the sediments at the bottom of the trench, where they've created complex communities that recycle nutrients and energy in ways that are completely different from surface ecosystems. Others live in the water column itself, forming the base of food webs that support all the larger creatures we've been talking about. What's absolutely fascinating is that many of these microorganisms are so specialized for deep-sea life that they literally cannot survive in normal surface conditions. Bring them up to shallow water, and they die just as quickly as a surface organism would die if brought to the deep ocean. These extremophiles have developed unique metabolic pathways that allow them to extract energy from chemical compounds rather than sunlight, essentially creating their own food sources through processes like chemosynthesis. Some species can break down sulfur compounds, others can process methane, and still others can derive energy from the breakdown of organic matter that's been falling from the surface for months or even years. The diversity of these microbial communities is staggering. Scientists estimate that a single cubic meter of deep-sea sediment might contain thousands of different species of microorganisms, most of which haven't even been discovered yet. Next up, let's dive into the world of barophilic bacteria. And yes, that's exactly what it sounds like, bacteria that love pressure. These microscopic organisms represent one of the most successful life strategies in the deep ocean, having evolved to not just tolerate crushing pressure, but actually require it to function properly. Barophilic bacteria have fundamentally different cellular structures compared to their surface-dwelling relatives. Their cell membranes are made of special lipids that remain flexible under pressure, while surface bacteria would have their membranes become rigid and non-functional. Their enzymes and proteins are designed to fold and function correctly only under high-pressure conditions. At surface pressure, these same proteins would unfold and become useless. Some barophilic bacteria have been found living at pressures over 100 times greater than surface pressure, making them among the most pressure-adapted life forms known to science. But here's what's really incredible. These bacteria are formed in complex communities and partnerships with other deep-sea organisms, creating symbiotic relationships that are crucial for life in the deep ocean. Many deep-sea animals, including some of the fish and invertebrates we've talked about, actually depend on barophilic bacteria living in their guts or other body tissues to help them digest food and process nutrients. The bacteria, in return, get a stable environment and a steady supply of nutrients from their host. These partnerships are so important that many deep-sea animals cannot survive without their bacterial symbionts. It's a perfect example of how life finds ways to cooperate and thrive even in the most challenging environments. Believe it or not, the food chains in the abyss operate by completely different rules than anything you'd find on land or in shallow water. Since there's no sunlight for photosynthesis, the entire ecosystem depends on what scientists call marine snow, a constant gentle rain of organic matter that drifts down from the surface layers of the ocean. This marine snow consists of dead plankton, fecal pellets, mucus, and other organic debris that slowly sinks through thousands of meters of water before reaching the bottom. The journey from surface to seafloor can take weeks or months, and much of this organic matter gets consumed or broken down along the way, so only a small fraction actually reaches the bottom. This makes the deep ocean floor one of the most food-scarce environments on Earth, where every scrap of nutrition is precious. The creatures living down there have evolved incredibly efficient ways to find, capture, and utilize this sparse food supply. Many organisms are what scientists call sit-and-wait predators. They position themselves strategically and wait for food to literally fall from the sky. Others are active scavengers, constantly patrolling the seafloor, looking for any edible debris. The food web is relatively simple compared to surface ecosystems, with just a few levels. The marine snow and organic debris form the base. Various bacteria and small invertebrates process this material, and larger predators, like fish and squid, feed on the smaller organisms. But here's the fascinating part. Because food is so scarce, many deep-sea organisms have evolved to be incredibly opportunistic. They can eat almost anything organic, and many species can go months or even years between meals, slowing their metabolism to a crawl until the next feeding opportunity comes along. Now, here's something that'll capture your imagination. Bioluminescence in the deep ocean is like nature's own light show, and it serves purposes that go far beyond just looking pretty. In the complete darkness of the deep sea, the ability to produce light becomes a crucial survival tool, and creatures have evolved some truly remarkable ways to use it. Many deep-sea organisms use bioluminescence for what scientists call counter-illumination. They produce light on their undersides that matches the faint glow filtering down from the surface, making them nearly invisible to predators looking up from below. Others use bioluminescent lures to attract prey in the darkness, essentially fishing with their own bodies as the bait. The anglerfish is probably the most famous example, with its glowing lure dangling in front of its mouth like a biological fishing rod. But the uses of bioluminescence go far beyond hunting and hiding. Many deep-sea creatures use patterns of lights to communicate with each other, flashing specific sequences to identify their species or signal their readiness to mate. Some organisms can produce different colors of light for different purposes. Blue light for long-distance communication, green light for close-range interactions, and red light for activities they want to keep hidden from other creatures that can't see red wavelengths. The chemistry behind deep-sea bioluminescence is fascinating in itself. Most organisms use a reaction between a chemical called luciferin and an enzyme called luciferase. But different species have evolved their own unique versions of these chemicals, producing lights with different colors, intensities, and durations. Some deep-sea creatures can even control their bioluminescence voluntarily, turning their lights on and off like biological flashlights, while others produce light continuously or only when disturbed. Let me tell you about something truly extraordinary. The evolutionary adaptations that allow life to exist in the Mariana Trench are so extreme that they represent some of the most dramatic examples of evolution in action on our planet. We're talking about organisms that have essentially redesigned their entire biology to function in an environment that would instantly kill their ancestors. Take pressure adaptation, for example. Deep-sea organisms have evolved completely different cellular structures, with flexible membranes, specialized proteins, and unique metabolic pathways that not only tolerate crushing pressure, but actually require it to function. Their proteins are folded in ways that would be impossible under normal pressure, and their cellular processes operate at rates and temperatures that would shut down surface life. But pressure is just one of many challenges these organisms have overcome. The complete absence of light has led to some truly remarkable adaptations. Many deep-sea creatures have enlarged eyes designed to capture even the faintest traces of bioluminescence, while others have abandoned vision entirely and developed enhanced chemical and vibrational senses that allow them to navigate and hunt in total darkness. The scarcity of food has driven the evolution of incredibly efficient metabolisms, with some organisms able to survive on as little as 1% of the food that their shallow water relatives require. Some deep-sea creatures have evolved the ability to slow their metabolism so dramatically that they can essentially put themselves into a state of suspended animation during times when food is particularly scarce. Others have developed the ability to eat prey much larger than themselves, or to digest materials that would be inedible to surface organisms. Speaking of remarkable adaptations, here's something that'll blow your mind about deep-sea reproduction. Many abyssal creatures have evolved mating strategies that seem almost science fiction-like in their strangeness. In an environment where finding a mate might be a once-in-a-lifetime opportunity, organisms have had to get creative. Some deep-sea anglerfish species have evolved a mating system where the tiny male essentially becomes a permanent parasite on the much larger female, fusing with her body and providing sperm whenever she needs it. The Dumbo octopus has evolved to be the ultimate opportunist. Females carry eggs in various stages of development, so they're always ready to mate when they encounter a male, and they can store sperm for long periods until environmental conditions are optimal for reproduction. Many deep-sea organisms have also evolved to reproduce multiple times throughout their lives, unlike their shallow water relatives that often die after a single reproductive event. This strategy makes sense in an environment where survival is already so challenging that every opportunity to pass on genes must be maximized. Some species have even evolved hermaphroditism, with individuals capable of functioning as both male and female depending on the circumstances, essentially doubling their chances of successful reproduction when they encounter another member of their species. The deep ocean has also produced some of the longest-lived organisms on Earth, with some deep-sea species living for hundreds or even thousands of years, giving them multiple opportunities to reproduce over their extended lifespans. Moving on to something particularly fascinating, let's talk about how deep-sea creatures have reinvented their entire sensory systems to function in an environment where traditional senses like sight become useless. Many abyssal organisms have developed incredibly sophisticated chemical sensing abilities, essentially tasting the water around them to detect prey, predators, or potential mates from great distances. The giant tube worms that live around hydrothermal vents can detect chemical gradients in the water that lead them to optimal feeding locations, while many deep-sea fish have evolved lateral line systems that are far more sensitive than those of surface fish, allowing them to detect the slightest water movements caused by nearby organisms. Some deep-sea creatures have evolved electroreception abilities, detecting the weak electrical fields generated by other living creatures. This is particularly useful in an environment where bioluminescence might give away your location to predators. The frilled shark, one of the most primitive sharks still living today, has evolved an incredibly sensitive lateral line system that allows it to detect water movements from prey animals hundreds of meters away. Many deep-sea organisms have also evolved enhanced touch sensitivity, with specialized appendages and sensory organs that can detect chemical trails, water movements, and vibrations that would be imperceptible to surface creatures. The result is a world where organisms navigate and interact through senses that are almost entirely foreign to surface life, creating ecosystems that operate by sensory rules we're only beginning to understand. Now, here's something truly remarkable about the diversity of life in the Mariana Trench. Scientists estimate that we've only discovered and cataloged a tiny fraction of the species that actually live there. Every expedition to the deep ocean reveals new species, new adaptations, and new ways that life has found to thrive in extreme conditions. In 2019 alone, researchers discovered over 30 new species during expeditions to various deep-sea locations, including several from the Mariana Trench. These discoveries are revolutionary for our understanding of life itself. Many deep-sea organisms use biochemical pathways and cellular processes that were previously unknown to science, and studying these creatures has led to breakthroughs in fields ranging from biotechnology to medicine. The enzymes used by deep-sea bacteria, for example, have found applications in industrial processes that require extreme conditions, while the pressure-resistant proteins found in deep-sea fish are being studied for their potential use in developing new materials and medical treatments. The bioluminescent chemicals produced by deep-sea organisms have been adapted for use in medical imaging and research, allowing scientists to track biological processes in living tissues with unprecedented precision. But perhaps most importantly, the study of deep-sea life is expanding our understanding of the possible limits of life itself, providing insights that may help us understand how life might exist on other planets or moons in our solar system. Let me share something that'll really put the uniqueness of deep-sea life in perspective. The creatures living in the Mariana Trench represent some of the most ancient lineages on our planet, essentially living fossils that have remained relatively unchanged for millions of years. The frilled shark, for example, is considered a living fossil that has retained characteristics of sharks that lived over 300 million years ago. Its primitive features, including its eel-like body and unusual gill structure, provide scientists with invaluable insights into early shark evolution. Similarly, the coelacanth-like features found in some deep-sea fish suggest evolutionary connections to ancient fish lineages that were thought to be extinct. This ancient heritage is possible because the deep ocean environment has remained relatively stable for millions of years, providing a kind of evolutionary time capsule where ancient life forms could persist while their shallow water relatives evolved or went extinct. But these organisms are also highly specialized for their extreme environment, representing millions of years of fine-tuning for life in the abyss. This combination of ancient heritage and extreme specialization makes deep-sea organisms uniquely valuable for understanding both the history of life on Earth and the potential future of life in extreme environments. As our planet's climate continues to change, The stable conditions of the deep ocean may become increasingly important as refuges for biodiversity, and the organisms that have already mastered life in these conditions may hold keys to understanding how life can adapt to changing environmental conditions. Here's something that might surprise you about the social behavior of deep-sea creatures. Despite living in one of the most isolated environments on Earth, many abyssal organisms have evolved complex social behaviors and communication systems. The supergiant amphipods we talked about earlier often gather in massive swarms that can contain thousands of individuals, working together to find and process food sources. These swarms show coordinated movement patterns and what appears to be information sharing about food sources and environmental conditions. Deep-sea jellyfish have been observed forming temporary aggregations that may serve both feeding and reproductive functions, with individuals coordinating their movements to maximize their feeding efficiency. Some deep-sea squid species engage in complex courtship behaviors involving bioluminescent displays and coordinated swimming patterns, essentially putting on light shows to attract mates in the darkness. Even more remarkably, some deep-sea organisms appear to engage in what scientists call facilitation, behaviors that help other species survive, even when there's no obvious benefit to the helper. For example, some deep-sea corals create structure and habitat that benefits numerous other species, while certain bacteria produce chemicals that help other organisms process nutrients or defend against pathogens. These social behaviors and cooperative relationships suggest that even in the most extreme environments, life finds ways to work together to overcome challenges that would be impossible for individual organisms to handle alone. Finally, let's talk about something truly mind-blowing: the role that deep-sea organisms play in global ocean processes and climate regulation. The creatures living in the Mariana Trench and other deep-sea environments are integral parts of systems that affect the entire planet. The bacterial communities in deep-sea sediments play crucial roles in processing carbon, nitrogen, and other elements that cycle through the global ocean system. Deep-sea organisms help sequester carbon from the atmosphere by consuming organic matter that sinks from the surface and incorporating it into their bodies or burying it in sediments where it can remain locked away for thousands of years. The vertical migrations of some deep-sea organisms, moving up and down through the water column on daily cycles, help transport nutrients between different ocean layers, supporting productivity in surface waters that ultimately affects global food webs and climate patterns. Some deep-sea bacteria produce compounds that affect the chemical composition of seawater, influencing everything from ocean pH to the availability of nutrients for surface plankton. The discovery of these connections has revolutionized our understanding of how ocean ecosystems function and highlighted the critical importance of protecting deep-sea environments. As we face global challenges like climate change and ocean acidification, the organisms living in places like the Mariana Trench may hold keys to understanding how ocean systems respond to environmental changes and how we might work with natural processes to maintain healthy ocean environments for the Mariana Peace future. Let's dive into the fascinating human story of how we discovered and explored the deepest place on Earth. The tale of Mariana Trench exploration reads like an adventure novel, filled with daring pioneers, technological breakthroughs, and the occasional spectacular failure. It all started on March 23, 1875, when the crew of HMS Challenger was conducting what they thought would be a routine depth measurement in the middle of the Pacific Ocean. Picture this: a Victorian-era sailing ship, complete with hemp ropes and weighted lines, accidentally stumbling upon the deepest place on our planet. The scientists aboard weren't looking for anything special. They were just following their standard procedure of taking depth soundings every 200 miles or so as part of the first truly scientific expedition to study the world's oceans. When they lowered their weighted rope at a spot about 175 miles southwest of Guam, something extraordinary happened. The rope kept going down and down and down. After what must have felt like an eternity, it finally hit bottom at an astounding 475 fathoms, nearly 27.0 feet, or about 5 miles deep. The crew was absolutely astonished. This was by far the deepest measurement of the nearly 500 depth soundings they had taken around the world. They repeated the experiment just to make sure, and sure enough, they got the same mind-boggling result. The immense water pressure at that depth actually crushed the thermometers attached to their sounding equipment. They named this mysterious deep spot Swire Deep after Herbert Swire, the ship's navigating sub-lieutenant, having no idea that they had just discovered what would later be recognized as the deepest accessible point on Earth. Moving forward in time, here's where the story gets even more incredible. It would be 85 years before anyone actually laid eyes on the bottom of what we now call Challenger Deep. On January 23, 1960, two remarkably brave men squeezed themselves into a specially designed pressure vessel called the Bathyscaphe Trieste and began what would become one of the most dangerous and significant journeys in human history. Don Walsh, a U.S. Navy lieutenant, and Jacques Piccard, a Swiss oceanographer and son of the Trieste's designer, spent nearly 5 hours descending through increasingly hostile waters toward the deepest point on Earth. The Trieste wasn't exactly what you'd call comfortable. Imagine being locked inside a steel sphere just over 2 meters in diameter, with walls 12.7 centimeters thick, designed to withstand pressure that would instantly crush a human body. The descent was harrowing from the start. As they dropped through the water column, they could hear the hull creaking and groaning under the increasing pressure. About 2/3 of the way down, they heard a loud crack that sounded like a gunshot. One of the outer windows had developed a crack due to the extreme conditions. For a moment, they considered aborting the mission, but after careful consideration, they decided the crack was in the outer window only and continued their descent. When they finally reached the bottom at 814 feet later, measurements would show they had actually reached about 797 feet. They found themselves in an alien landscape of fine sediment and complete darkness. Through their porthole, illuminated by their floodlights, they observed what Piccard later described as a waste of firm, diatomaceous ooze. But here's the kicker. They thought they saw a flatfish lying on the seafloor, about a foot long, which would have been revolutionary proof that complex life could exist at such depths. Modern scientists now believe they probably saw a sea cucumber, but at the time, it was groundbreaking evidence that life could exist even in Earth's most extreme environment. Next up, let's talk about what might be the most technologically ambitious solo adventure in human history, James Cameron's 2012 dive to Challenger Deep. You know Cameron as the director of Titanic and Avatar, but what you might not realize is that he's also a serious ocean explorer with a passion for deep-sea technology. On March 26, 2012, Cameron squeezed himself into a lime green submersible called Deep Sea Challenger and embarked on a journey that would make him the first person to reach the bottom of the Mariana Trench solo. The Deep Sea Challenger was like something out of a science fiction movie, a vertical torpedo-shaped vehicle designed specifically for this one incredible mission. Unlike the spherical Trieste, Cameron's sub was designed more like a rocket ship, with Cameron sitting in a pilot sphere at the bottom while the rest of the vehicle was packed with cameras, lights, and scientific equipment. The descent took 2 hours and 36 minutes, during which Cameron became increasingly isolated from the world above as he dropped through the ocean's layers. When he reached the bottom at 787 feet, he found himself in what he described as a desolate, lunar-like landscape covered in fine sediment. He had planned to spend about 6 hours exploring the bottom, but his mission was cut short when a hydraulic fluid leak obscured his view and caused him to lose control of his starboard thrusters. Still, during his brief time on the seafloor, he collected samples and shot footage that gave the world its first high-definition look at the deepest place on Earth. Cameron later described the experience as both humbling and surreal, being alone in a place where only 2 other humans had ever been, surrounded by crushing pressure and absolute darkness, yet feeling a profound connection to the planet and the incredible forces that shaped it. Here's something that might surprise you about deep-sea exploration. Some of the most important discoveries have come from unmanned vehicles that can stay down longer and go places too dangerous for human crews. The Japanese remotely operated vehicle Kaiko was one of these robotic pioneers, making its first descent to Challenger Deep in 1996, nearly 4 decades after the Trieste's historic dive. Kaiko was revolutionary because it could spend hours on the seafloor, collecting samples and taking detailed photographs without risking human lives. During its multiple dives to the deepest parts of the trench, Kaiko discovered something that changed our understanding of deep-sea life: mud samples that contained nearly 200 different species of microorganisms. This was proof that even in the most extreme conditions on Earth, life not only survived but thrived in incredible diversity. The robot also collected the first clear photographs of the strange creatures living at these depths, including the bizarre xenophyophores and amphipods we talked about earlier. Tragically, Kaiko was lost at sea in 2003 during a typhoon, but its legacy lives on in the scientific knowledge it gathered. Following Kaiko's success, other unmanned vehicles continued the exploration. The American hybrid, remotely operated vehicle Nereus reached Challenger Deep in 2009, becoming the first vehicle to return to the deepest point in nearly 50 years. Nereus was designed to operate both as a free-swimming autonomous vehicle and as a tethered ROV, giving it unprecedented flexibility in exploring the deep ocean. During its dives, Nereus collected sediment samples and captured video footage that revealed the dynamic nature of life at the bottom of the trench. Like Kaiko before it, Nereus met an unfortunate end when it imploded during a dive in 2014, a stark reminder of just how challenging deep-sea exploration remains, even with modern technology. Believe it or not, the story of Mariana Trench exploration has become increasingly international in recent years, with China emerging as a major player in deep-sea exploration. In November 2020, the Chinese submersible Fenduge, which means striver in English, carried 3 Chinese scientists to the bottom of Challenger Deep, making China only the second country after the United States to successfully conduct a manned dive to the deepest point on Earth. The Fenduge dive was particularly significant because it was broadcast live on Chinese television, allowing millions of people to witness the journey to the bottom of the ocean in real time. The submersible, with its distinctive red and white color scheme, was designed to carry a 3-person crew and was equipped with advanced cameras and sampling equipment made by Norwegian manufacturers. During their dive to 35,791 feet, the Chinese crew collected samples of water, sediment, and marine life, while also conducting experiments to study the behavior of materials under extreme pressure. The mission was part of China's broader strategy to become a leader in deep-sea research and exploration. The Chinese team spent considerable time at the bottom, demonstrating their submersible's reliability and capability for extended operations in the most extreme environment on Earth. Japan has also continued its deep-sea exploration efforts with vehicles like the Kuroshio, and their scientists have made numerous discoveries about the geological processes that continue to shape the trench. These international efforts have turned deep-sea exploration into a new kind of space race, with countries competing to push the boundaries of human knowledge and technological capability in Earth's final frontier. Now, let's talk about something truly remarkable: the recent achievements of Victor Vescovo and his submersible limiting factor, which have revolutionized our understanding of what's possible in deep-sea exploration. Starting in 2019, Vescovo embarked on what he called the 5 Deeps expedition, with the goal of visiting the deepest point in each of the world's 5 oceans. His custom-built submersible, the DSV limiting factor, was designed to be the ultimate deep diving machine, capable of reaching any depth in the ocean and making repeated dives safely. On April 28, 2019, Vescovo reached a record-breaking depth of 35,853 feet in Challenger Deep, officially making him the deepest diving human in history. But here's what makes Vescovo's achievement truly extraordinary. He didn't just make one dive and call it quits. Between 2019 and 2022, he made a total of 15 dives to Challenger Deep, more than doubling the total number of human visits to the deepest point on Earth. Each dive revealed new information about the trench's topography, geology, and marine life. During one dive, Vescovo and his team discovered that the bottom of Challenger Deep isn't flat as previously thought, but consists of rocky ridges and depressions that create a complex underwater landscape. They also made the unfortunate discovery of human-made pollution at the bottom of the trench, including a plastic bag and candy wrappers. Stark evidence that human impact reaches even the most remote places on our planet. Perhaps most importantly, Vescovo's repeated dives demonstrated that with the right technology and careful engineering, human exploration of the deep ocean could become routine rather than exceptional. His submersible was so well designed that it allowed other explorers to visit Challenger Deep, including Catherine Sullivan, the first woman and first astronaut to reach the deepest point, and Kelly Walsh, the son of Don Walsh, making them the first father and son team to both visit the bottom of the ocean. Here's something you might not expect. The history of deep-sea exploration is filled with spectacular failures and near disasters that remind us just how challenging it is to explore the deepest parts of our planet. The ocean depths are so hostile to human technology that even the most carefully designed equipment can fail catastrophically. We already mentioned the loss of Kaiko and Nereus, but there have been many other setbacks and close calls. During the Trieste dive in 1960, the cracked window could have been catastrophic. If the inner window had failed, Walsh and Pickard would have been killed instantly. James Cameron's deep-sea Challenger suffered multiple system failures during its dive, and Cameron later admitted that there were several moments when he wasn't sure he would make it back to the surface. The hydraulic leak that shortened his mission could have been much worse if it had affected critical systems like life support or ballast control. Even modern submersibles face constant challenges. The limiting factor, despite its advanced design, has experienced equipment failures, communication problems, and navigation difficulties during its dives. The extreme pressure, corrosive seawater, and complete darkness create an environment where even the smallest malfunction can become life-threatening. Many planned expeditions have been canceled or postponed due to equipment failures, bad weather, or funding problems. The cost of deep-sea exploration is enormous. A single dive to Challenger Deep can cost hundreds of thousands of dollars, and that's assuming everything goes according to plan. When you factor in the years of preparation, the specialized equipment, the support vessels, and the highly trained crews, the total cost of a deep-sea expedition can easily reach millions of dollars. This economic reality means that deep-sea exploration remains limited to a few wealthy individuals, government agencies, and well-funded research institutions, keeping the deepest parts of our planet accessible to only a select few. Moving on to the technological evolution of deep-sea exploration, it's absolutely fascinating to see how far we've come since that first hemp rope was lowered from HMS Challenger in 1875. The progression from weighted ropes to echo sounders to multi-beam sonar to pressure-resistant submersibles represents one of the most impressive technological achievements in human history. In the early days, depth measurement was a laborious and inaccurate process that required stopping the ship and lowering a weighted line until it hit bottom. This method could take hours and was subject to errors caused by ocean currents, wind, and the difficulty of determining exactly when the weight reached the seafloor. The introduction of echo sounding in the 1920s revolutionized ocean exploration by allowing ships to measure depth while moving, using sound waves that bounced off the seafloor and returned to the surface. This technology enabled the creation of the first detailed maps of ocean basins and revealed the true extent of features like the Mariana Trench. The development of multi-beam sonar in the 1970s and 1980s allowed researchers to map large areas of the seafloor with unprecedented detail, revealing the complex topography of deep ocean trenches. Modern sonar systems can create three-dimensional maps of the seafloor that are more detailed than many maps of terrestrial landscapes. The evolution of submersible technology has been equally impressive. The Trieste was essentially a steel ball attached to a float filled with gasoline, with very limited mobility and virtually no scientific equipment. Modern submersibles, like the limiting factor, are marvels of engineering, with sophisticated life support systems, powerful thrusters for precise maneuvering, advanced cameras and lighting systems, robotic arms for collecting samples, and computer-controlled ballast systems that allow for precise depth control. The materials used in these vehicles have also evolved dramatically, with modern submersibles utilizing titanium alloys, syntactic foam, and other advanced materials that can withstand crushing pressure while remaining lightweight enough for practical operation. Here's where things get really exciting. The future of Mariana Trench exploration promises to bring us discoveries and capabilities that would have been pure science fiction just a few decades ago. Several countries and private organizations are currently developing new technologies that could revolutionize our understanding of the deep ocean. China is working on advanced autonomous underwater vehicles that could remain in the deep ocean for months at a time, continuously collecting data and samples without human intervention. These robots would be powered by radioisotope thermoelectric generators, the same power source used in space probes, allowing them to operate in the deep ocean for years without returning to the surface. Japan is developing new materials and construction techniques that could make deep-sea vehicles cheaper and more reliable, potentially opening up routine access to the deepest parts of the ocean. The United States is investing in research into artificial intelligence systems that could make autonomous exploration vehicles more capable of making independent decisions about where to go and what to study. Private companies are also getting involved, with several organizations planning commercial deep-sea exploration services that could make trips to places like Challenger Deep available to researchers, adventurers, and even tourists who can afford the substantial cost. Some visionary engineers are even proposing the construction of permanent research stations on the bottom of deep ocean trenches, similar to research stations in Antarctica, where scientists could live and work for extended periods while studying the deep-sea environment. These underwater habitats would need to be incredibly sophisticated, with closed-loop life support systems, nuclear or geothermal power sources, and regular supply runs from the surface. While such projects remain largely theoretical, the rapid pace of technological development suggests that permanent human presence in the deep ocean may not be as far-fetched as it once seemed. You might be surprised to learn that one of the most significant recent developments in deep-sea exploration has been the democratization of deep ocean access through advanced remotely operated vehicles and autonomous underwater vehicles. While human-rated submersibles remain incredibly expensive and risky, robotic explorers are becoming more capable and affordable every year. Modern ROVs can be controlled from research vessels on the surface via fiber optic cables, allowing scientists to explore the deep ocean with unprecedented safety and flexibility. These robots can stay underwater for days or weeks at a time, collecting samples, taking photographs, and conducting experiments without putting human lives at risk. Autonomous underwater vehicles, or AUVs, represent an even more exciting development. These robots can be programmed with specific missions and released to explore areas of the deep ocean completely independently, making decisions about where to go and what to study based on their onboard artificial intelligence systems. Some AUVs are designed to drift with ocean currents for months or years, collecting data on water chemistry, temperature, and marine life as they travel across entire ocean basins. Others are equipped with sophisticated sensors that can detect and study geological processes like underwater earthquakes and volcanic eruptions. The data collected by these robotic explorers is transmitted to scientists around the world via satellite communication, allowing researchers to study the deep ocean in real time from their laboratories. This technological revolution means that our understanding of places like the Mariana Trench is advancing more rapidly than ever before, with new discoveries being made on an almost daily basis. The combination of human-crewed submersibles for complex scientific missions and robotic vehicles for routine exploration and monitoring is creating a comprehensive approach to deep-sea research that was unimaginable just a generation ago. Finally, let's talk about something that really puts the future of deep-sea exploration into perspective: the growing recognition that understanding our deep oceans is crucial for understanding and protecting our entire planet. The Mariana Trench and other deep-sea environments play critical roles in global climate regulation, carbon sequestration, and marine ecosystem health. As we face challenges like climate change, ocean acidification, and marine pollution, the deep ocean is becoming increasingly important as both a refuge for marine life and a key component of Earth's climate system. Future exploration missions will focus not just on discovery for its own sake, but on understanding how deep-sea environments interact with global systems and how we can protect these crucial ecosystems. Scientists are planning long-term monitoring programs that will use networks of sensors and robotic vehicles to track changes in deep-sea environments over decades or centuries. These programs will help us understand how the deep ocean responds to climate change and other human impacts, and may provide early warning signs of changes that could affect the entire planet. Some researchers are even proposing that the deep ocean could play a role in climate change mitigation through projects like deep-sea carbon sequestration or the harvesting of deep-sea resources for renewable energy technologies. However, these potential applications raise important questions about how to balance scientific advancement with environmental protection. The history of Mariana Trench exploration teaches us that the deep ocean is both incredibly resilient and surprisingly fragile, capable of supporting unique life forms, but also vulnerable to human impacts that can reach even the most remote places on Earth. As we continue to push the boundaries of deep-sea exploration, we're also learning that our responsibility as explorers extends beyond discovery to stewardship, ensuring that future generations will be able to study and appreciate these remarkable environments that represent some of the last frontiers on our planet. The Mariana Trench is the result of one of the most dramatic geological processes on our planet. Picture this. Imagine two massive conveyor belts made of solid rock, each the size of a continent, slowly but inexorably colliding with each other. That's essentially what's happening beneath the Mariana Trench, where the Pacific Plate is diving beneath the smaller Philippine Sea Plate in a process called subduction. This isn't a gentle process. We're talking about chunks of the Earth's crust that are dozens of kilometers thick and thousands of kilometers across, grinding against each other with forces that are almost incomprehensible. The Pacific Plate, which is older and denser than the Philippine Sea Plate, gets pushed down into the Earth's mantle like a massive geological bulldozer. As it descends, it creates the characteristic V-shaped profile that we see in ocean trenches. But here's what makes this process truly mind-blowing. The Pacific Plate is bending and flexing under enormous stress, creating fractures and deformation that extend for hundreds of kilometers in all directions. The plate bends so dramatically that it actually forms what geologists call a flexural moat, a depression that runs parallel to the trench where the plate starts to bend downward. This bending process generates enormous amounts of heat and pressure, which drives many of the other geological processes we see in the region. The subduction zone at the Mariana Trench is particularly active and well-developed because the Pacific Plate here is some of the oldest oceanic crust on Earth, up to 170 million years old, making it cold, dense, and heavy enough to sink readily into the underlying mantle. Now, here's something that'll really capture your imagination about the Philippine Sea Plate dynamics. This smaller plate is essentially caught in a geological squeeze play between several much larger plates, creating a complex and highly active tectonic environment. The Philippine Sea Plate is like a relatively small piece in a massive geological puzzle, surrounded by the Pacific Plate to the east, the Eurasian Plate to the west and north, and the Indo-Australian Plate to the south. This unique position makes it one of the most tectonically active regions on Earth, with multiple subduction zones operating simultaneously around its borders. At the Mariana Trench, the Philippine Sea Plate is the overriding plate, meaning it sits on top of the subducting Pacific Plate. But here's the fascinating part. The Philippine Sea Plate itself is also being subducted along its western margin, where it dives beneath the Eurasian Plate. This creates a situation where the Philippine Sea Plate is simultaneously acting as both an overriding plate and a subducting plate, depending on which direction you're looking. This complex tectonic setting is what makes the Mariana region so geologically diverse and active. The stresses generated by this multi-directional plate motion create a constantly changing landscape of volcanic islands, underwater mountains, and deep ocean trenches. The movement isn't uniform either. Different parts of the Philippine Sea Plate are moving at different rates and in slightly different directions, creating internal stresses that generate earthquakes and volcanic activity throughout the region. Geologists estimate that the Philippine Sea Plate formed relatively recently in geological terms, probably beginning around 50 million years ago, making it a young and dynamic piece of oceanic crust that's still evolving and changing shape as it responds to the forces acting on it from all sides. Moving on to something that might surprise you, the earthquake activity associated with the Mariana Trench is absolutely staggering in both frequency and intensity. The subduction process that creates the trench also makes it one of the most seismically active regions on our planet, with thousands of earthquakes occurring every year. Most of these are small tremors that go unnoticed except by sensitive seismic equipment, but the region also generates some of the largest and deepest earthquakes on Earth. Here's what's really fascinating about Mariana Trench earthquakes. They occur at depths that would be impossible in most other tectonic settings. While typical earthquakes happen within the first 20-30 kilometers of the Earth's crust, earthquakes in subduction zones like the Mariana Trench can occur at depths of 600 kilometers or more as the descending plate continues to fracture and deform deep within the Earth's mantle. These deep earthquakes are particularly interesting to scientists because they provide insights into conditions and processes that occur far beneath the Earth's surface, in regions that we can never directly explore. The earthquake patterns also tell us about the shape and behavior of the subducting plate as it descends into the mantle. By analyzing the location, depth, and magnitude of earthquakes over time, geologists can create three-dimensional maps showing how the Pacific Plate is bending and breaking as it sinks into the Earth's interior. Some of these earthquakes are truly massive. The region has generated earthquakes with magnitudes exceeding 8, which are among the most powerful seismic events on our planet. These large earthquakes can trigger tsunamis that affect coastlines throughout the Pacific Ocean, making the Mariana Trench region not just scientifically important, but also a significant natural hazard that affects millions of people living around the Pacific Rim. Here's where things get really spectacular. The volcanic features associated with the Mariana Trench create some of the most dramatic underwater landscapes on our planet. The subduction process also generates intense volcanic activity that builds underwater mountains, volcanic islands, and complex seafloor terrain. As the Pacific Plate descends into the mantle, it carries with it water trapped in minerals and sediments. When this water-rich material reaches depths of 100-200 kilometers and temperatures of 1,000 degrees Celsius or more, the water is released and rises into the overlying mantle rock. Water dramatically lowers the melting point of rock, so this released water causes the mantle to partially melt, creating magma that's less dense than the surrounding solid rock. This magma rises toward the surface, creating what geologists call a volcanic arc, a chain of volcanoes that parallels the trench. The Mariana Islands themselves are the surface expression of this volcanic arc, representing just the tips of massive underwater mountains that rise from the ocean floor. But the real action happens underwater, where active volcanic vents, lava flows, and hydrothermal systems create a constantly changing landscape of geological features. Some of these underwater volcanoes are enormous, larger than many terrestrial mountains, yet they remain completely hidden beneath thousands of meters of ocean water. The volcanic activity isn't limited to simple cone-shaped volcanoes either. The complex interactions between magma, seawater, and seafloor sediments create unique volcanic features like pillow lavas, volcanic glass formations, and explosive underwater eruptions that can alter the seafloor topography over periods of just days or weeks. Recent surveys have discovered active lava lakes on the seafloor, underwater volcanic explosions, and vast fields of volcanic debris that demonstrate just how geologically active this region remains today. Now let's talk about something that might blow your mind. The sediment layers at the bottom of the Mariana Trench contain a geological record that spans millions of years of Earth's history. These sediments are like pages in a book that tell the story of our planet's past climate, ocean conditions, and even major catastrophic events. The sediments come from several different sources, each contributing its own chapter to this geological story. Some sediments are the remains of microscopic marine organisms that lived in the surface waters and slowly drifted down to the seafloor after they died. These biological sediments, called biogenic oozes, can tell us about past ocean temperatures, chemistry, and the types of life that existed millions of years ago. Other sediments come from terrestrial sources: dust blown from continents, volcanic ash from eruptions around the Pacific Ring of Fire, and even cosmic dust from meteorite impacts and cometary debris. The deepest sediment layers in the Mariana Trench are probably tens of millions of years old, representing an almost unimaginably long period of slow accumulation. But here's what's really fascinating. The extreme depth of the trench means that these sediments have been preserved in conditions that exist nowhere else on Earth. The high pressure, low temperature, and lack of oxygen create a natural time capsule where organic matter decomposes extremely slowly and chemical processes that would destroy evidence of past events are inhibited. Scientists studying these sediments have found evidence of ancient climate changes, massive volcanic eruptions, and even asteroid impacts that affected the entire planet. The sediment layers also show evidence of the ongoing tectonic processes that continue to shape the trench. Layers that have been folded, faulted, and deformed by the immense geological forces acting in this region. By drilling core samples from these sediment layers, researchers can reconstruct a detailed history of the Western Pacific region that extends back to when the dinosaurs roamed the Earth. Here's something truly remarkable about the tectonic movement rates in the Mariana region. We can actually measure the plates moving in real time using modern GPS and satellite technology. The Pacific Plate is moving toward the northwest at a rate of about 9 centimeters per year relative to the Philippine Sea Plate. That might not sound like much, but remember that these are pieces of the Earth's crust, the size of continents, and they've been moving at this rate for millions of years. To put this in perspective, 9 centimeters per year is about the same rate that your fingernails grow, but when you multiply that by millions of years, you get movement measured in thousands of kilometers. The movement isn't perfectly uniform either. GPS measurements show that different parts of the plate boundary are moving at slightly different rates, creating internal stresses that contribute to the complex pattern of earthquakes and volcanic activity in the region. The convergence rate has probably varied over geological time, speeding up and slowing down in response to changes in global tectonic forces and the thermal evolution of the Earth's interior. Faster convergence rates tend to create deeper trenches and more intense volcanic activity, while slower rates allow sediments to fill in the trench and reduce its depth. The current convergence rate at the Mariana Trench is considered relatively fast compared to other subduction zones around the world, which helps explain why the Mariana Trench is the deepest oceanic trench on our planet. But here's the really cool part. We can use these movement rates to predict future changes in the region. Over the next million years, the Pacific Plate will continue to dive beneath the Philippine Sea Plate, potentially making the Mariana Trench even deeper while continuing to build the volcanic arc that creates the Mariana Islands. However, tectonic processes can change unpredictably, and major reorganizations of plate boundaries have occurred throughout Earth's history. so while we can make educated guesses about the future, the geological evolution of the region will almost certainly surprise us in ways we can't currently imagine. Moving on to something that'll really fascinate you, the mineral formations in the Mariana Trench region represent some of the most unique and economically important geological features on our planet. The combination of extreme pressure, high temperature, and active volcanic processes creates conditions where unusual minerals can form that are found nowhere else on Earth. The subduction process concentrates and transforms minerals in ways that create deposits of rare earth elements, precious metals, and other valuable materials. Some of the most interesting mineral formations are associated with the hydrothermal vents that dot the seafloor around the trench. These underwater hot springs create chimney-like structures made of sulfide minerals that can contain significant concentrations of copper, zinc, gold, and silver. The extreme conditions at these vents, temperatures exceeding 400 degrees Celsius and highly acidic, mineral-rich water, create a natural laboratory where new minerals are constantly forming and dissolving. Scientists have discovered mineral species at Mariana Trench, hydrothermal vents that were previously unknown to science, expanding our understanding of the range of conditions under which different minerals can form. The sediments surrounding these vents are also enriched in rare earth elements and other valuable materials, creating what some geologists call seafloor massive sulfide deposits that could potentially be mined in the future. But it's not just the hydrothermal vents that create interesting mineral formations. The subduction process itself concentrates certain elements in specific zones, creating deposits of materials like manganese nodules, potato-shaped concretions that grow slowly on the seafloor over millions of years. These nodules contain not just manganese, but also cobalt, nickel, and rare earth elements that are crucial for modern technology. The extreme pressure conditions in the deepest parts of the trench also create unique crystal structures and mineral phases that can only form under such conditions, providing insights into the behavior of materials under pressures that exist deep within planetary interiors. Now, here's something that'll truly capture your imagination. The hydrothermal vents around the Mariana Trench create some of the most alien and spectacular environments on our planet. These underwater geysers form where seawater seeps down through cracks in the seafloor and comes into contact with hot volcanic rocks, getting superheated and picking up dissolved minerals before shooting back up through the seafloor like underwater volcanoes. The water that emerges from these vents can reach temperatures of over 400 degrees Celsius, hot enough to melt lead, and is loaded with dissolved minerals that immediately precipitate when they hit the cold seawater, creating towering chimney-like structures that can grow several meters tall in just a few years. The Mariana region hosts several different types of hydrothermal vents, each with its own unique characteristics. Some vents, called black smokers, emit dark clouds of mineral-rich water that look like underwater smokestacks. Others, known as white smokers, emit lighter-colored plumes rich in different mineral compositions. Some of the most unusual vents in the Mariana region emit liquid carbon dioxide and create what scientists call champagne vents because of the bubbles that rise from them. These vents are also oases of life in the deep ocean. The chemical energy produced by the interaction between hot volcanic rock and seawater supports entire ecosystems of organisms that exist nowhere else on Earth. Giant tube worms, unique species of crabs and shrimp, and countless varieties of bacteria and archaea thrive around these vents, creating biological communities that are completely independent of sunlight and photosynthesis. The discovery of these hydrothermal vent ecosystems revolutionized our understanding of the limits of life and has important implications for astrobiology, as similar environments might exist on other planets and moons in our solar system. Here's something that really puts the geological complexity of the Mariana region into perspective. The trench system actually consists of multiple interconnected trenches, ridges, and basins that create one of the most geologically diverse regions on our planet. The main Mariana Trench is just one part of a larger system that includes back-arc basins, volcanic ridges, and transform faults that create a complex three-dimensional structure beneath the ocean. The back-arc region, located between the main volcanic arc and the larger landmasses to the west, is characterized by active seafloor spreading similar to what occurs at mid-ocean ridges. This creates new oceanic crust, while the main trench is consuming old oceanic crust through subduction, making the region a natural laboratory for studying both constructive and destructive plate tectonic processes simultaneously. The transform faults that cut across the region create additional complexity, allowing different sections of the plate boundary to move at different rates and in different directions. These faults can generate large earthquakes and create linear valleys and ridges that add to the already complex topography of the region. The interaction between all these different geological processes creates a constantly changing landscape, where new features are forming, while old ones are being destroyed or modified. Recent detailed mapping of the region has revealed seamounts, underwater canyons, and other features that demonstrate just how geologically active and diverse this region really is. Some areas show evidence of recent volcanic activity, while others display signs of large-scale submarine landslides or tectonic deformation that has occurred over thousands or millions of years. The geological complexity of the Mariana region makes it one of the most scientifically interesting places on Earth, where researchers can study a full range of tectonic processes operating simultaneously in a relatively small area. Now, let's talk about something that really drives home the ongoing nature of geological processes in the Mariana region. The trench system is still actively evolving and changing today. Unlike many geological features that formed in the distant past and are now essentially static, the Mariana Trench is a dynamic, living system where geological processes are actively shaping the landscape in real time. Earthquakes occur daily, volcanoes erupt periodically, new hydrothermal vents form while old ones shut down, and the seafloor topography changes measurably over periods of just years or decades. Advanced sonar mapping, conducted just a few years apart, has shown changes in the depth and shape of parts of the trench, demonstrating that even the deepest parts of our oceans are not permanent features but are constantly being modified by ongoing geological processes. The sediment, transport, and deposition patterns are also constantly changing in response to earthquakes, volcanic eruptions, and changes in ocean currents, creating a dynamic environment where the geological record is being written in real time. Climate change and human activities are also beginning to affect the geological processes in the region, as changes in ocean temperature and chemistry alter the behavior of hydrothermal systems and the rates at which certain minerals form and dissolve. The increasing acidity of seawater due to carbon dioxide absorption is changing the chemistry of hydrothermal vents and affecting the mineral compositions of the formations they create. This ongoing evolution means that the Mariana Trench region will continue to surprise and challenge our understanding of geological processes, serving as a natural laboratory where we can study the fundamental forces that shape our planet. Future research will undoubtedly reveal new aspects of the geological processes operating in this remarkable region, adding new chapters to our understanding of how tectonic forces continue to shape the Earth we live on. Here's something that might blow your mind. Research in the Mariana Trench is helping us understand global climate patterns in ways that could reshape how we predict and respond to climate change. The deep ocean acts like a massive conveyor belt for heat and carbon, and the Mariana Trench sits at a crucial junction in this global system. Scientists have discovered that the deep waters in the trench contain some of the oldest water masses on Earth, water that hasn't been in contact with the atmosphere for over 10 years. This ancient water carries chemical signatures that tell us about past climate conditions, essentially giving us a window into Earth's climate history that extends back centuries before humans started keeping detailed weather records. But here's where it gets really fascinating. The trench also plays an active role in current climate regulation. The extreme depths create unique pressure and temperature conditions that affect how carbon dioxide dissolves and is stored in seawater. Deep-sea trenches like the Mariana may be acting as massive carbon sinks, pulling carbon dioxide out of the atmosphere and locking it away in the deep ocean for hundreds or thousands of years. Recent studies have found that the microbial communities living in the trench sediments are actively processing carbon in ways that scientists are only beginning to understand. Some of these microorganisms can break down organic carbon and convert it into forms that remain trapped in the deep ocean for geological timescales, potentially playing a crucial role in regulating atmospheric carbon dioxide levels. Understanding these processes could be key to predicting how our climate system will respond to continued carbon emissions, and might even point toward new strategies for carbon sequestration and climate change mitigation. Moving on to something that's both heartbreaking and eye-opening, the discovery of pollution in the deepest parts of our oceans has fundamentally changed how we think about human impact on the planet. You might assume that a place 7 miles underwater would be pristine and untouched by human activity, but you'd be wrong. In 2019, explorer Victor Vescovo made a shocking discovery during his record-breaking dive to Challenger Deep: a plastic bag and candy wrappers sitting on the seafloor at the deepest point on Earth. This subsequent research has revealed that plastic pollution has reached even the most remote parts of our oceans. Scientists studying amphipods collected from the deepest parts of the Mariana Trench found that 100% of the specimens contained microplastics in their digestive systems. Think about that for a moment. Creatures living in the most isolated environment on our planet, places that have been cut off from the surface world for millions of years, are now contaminated with human-made materials. But the pollution problem goes far beyond just plastics. Researchers have found elevated levels of persistent organic pollutants, or POPs, in the fatty tissues of deep-sea creatures. These include chemicals like PCBs and PBDEs, which were banned decades ago but continue to persist in the environment. The concentrations of these toxic chemicals in deep-sea organisms are actually higher than in many surface-dwelling creatures, demonstrating how pollutants can concentrate and accumulate as they sink through the ocean depths. Perhaps most disturbing of all, scientists have detected carbon-14 from nuclear weapons testing in the bodies of deep-sea organisms, showing that even radioactive contamination from the 1950s and 1960s has found its way to the deepest parts of our oceans. These discoveries have forced us to confront the sobering reality that there is no place on Earth that remains untouched by human activity, and they've sparked new research into how pollutants travel through ocean systems and accumulate in deep-sea environments. Here's something truly exciting that'll capture your imagination. The Mariana Trench continues to be a hotspot for discovering new species that expand our understanding of life's incredible diversity and adaptability. Since systematic exploration of the trench began, scientists have discovered dozens of new species, and they estimate that hundreds more remain to be found. In 2017, researchers discovered the Mariana snailfish, Pseudolaparus swirei, which holds the record as the deepest living fish known to science. But that's just the tip of the iceberg. Recent expeditions have uncovered new species of amphipods with unique adaptations for extreme pressure, including the remarkable discovery of amphipods that use aluminum to strengthen their exoskeletons, the first known organisms to use this metal for structural purposes. Scientists have also discovered new species of sea cucumbers, including one that floats in the water column rather than crawling on the sea floor, representing a completely different ecological niche in the deep ocean. The microbial discoveries are even more spectacular. Researchers have found entirely new groups of bacteria and archaea that use biochemical pathways never before seen in nature. Some of these microorganisms can survive and reproduce under pressures that would instantly kill any previously known life form, while others have evolved unique metabolic processes that allow them to extract energy from chemical compounds that would be toxic to most other organisms. In 2019, scientists discovered a new virus at a depth of 900 meters, making it the deepest located virus ever found. This bacteriophage, a virus that infects bacteria, represents an entirely new branch of viral evolution that has been isolated in the deep ocean for potentially millions of years. Each new species discovery not only adds to our catalog of Earth's biodiversity, but also provides new insights into the evolutionary processes that allow life to adapt to extreme conditions, with implications for understanding life's limits and potential existence in similar extreme environments elsewhere in the universe. Now, let's talk about something that's revolutionizing our understanding of Earth's history. The geological timeline insights we're gaining from Mariana Trench research are rewriting textbooks about how our planet has evolved over millions of years. The sediment layers at the bottom of the trench contain a remarkably detailed record of geological and environmental changes that extends back tens of millions of years. By analyzing cores drilled from these deep-sea sediments, scientists can reconstruct ancient ocean conditions, climate patterns, and even major catastrophic events with unprecedented precision. The trench sediments have preserved evidence of massive volcanic eruptions, asteroid impacts, and dramatic climate shifts that affected the entire planet. But here's what makes the Mariana Trench particularly valuable for geological research. Its extreme depth means that sediments deposited there have been preserved under conditions that exist nowhere else on Earth. The high pressure, low temperature, and lack of oxygen create an environment where organic matter decomposes extremely slowly, and chemical processes that would normally destroy geological evidence are inhibited. This natural preservation system has allowed scientists to recover intact molecular fossils and chemical signatures that provide direct evidence of environmental conditions from millions of years ago. Recent analysis of trench sediments has revealed evidence of ancient sea level changes ocean chemistry variations, and even changes in the Earth's magnetic field that occurred long before humans existed. The research has also provided new insights into the timing and causes of major extinction events, including the asteroid impact that killed the dinosaurs 66 million years ago. By comparing the geological record preserved in the Mariana Trench with similar records from other parts of the world, scientists are developing a more complete and accurate picture of how Earth's systems have changed over geological time, providing crucial context for understanding current environmental changes and predicting future conditions. Here's something you might find fascinating about the Mariana Trench's role in the global water cycle. This remote location is actually a crucial component in the planet-wide circulation of water that affects weather, patterns, and climate around the world. The trench sits at the intersection of several major ocean current systems, and the extreme depth creates unique conditions that influence how water masses move through the global ocean. Deep water formation processes that occur in polar regions eventually reach places like the Mariana Trench, where the water can remain trapped for centuries or millennia before eventually returning to the surface through upwelling processes in other parts of the world. But the trench actively processes water through interactions with hot volcanic rocks and hydrothermal systems. Water that seeps down into the seafloor around the trench gets heated and chemically modified before being expelled through hydrothermal vents, creating a natural water treatment system that affects the chemistry of the entire ocean basin. The subduction process itself also plays a role in the global water cycle by carrying water trapped in oceanic crust and sediments down into the Earth's mantle, where it eventually gets recycled back to the surface through volcanic processes. Scientists estimate that subduction zones like the Mariana Trench cycle billions of tons of water through the Earth's interior every year, making them a crucial but often overlooked component of the global hydrological cycle. Recent research has shown that changes in deep-sea circulation patterns can affect surface weather patterns and climate on timescales, ranging from years to centuries, highlighting the importance of understanding these deep ocean processes for predicting future climate conditions. The discovery of unique water masses and circulation patterns in the trench region has also provided new insights into how ocean circulation might change in response to global warming, with potentially significant implications for regional and global climate patterns. Moving on to something truly groundbreaking, the seismic monitoring capabilities we've developed around the Mariana Trench have transformed our ability to understand and predict earthquakes, not just in the region, but around the entire Pacific Rim. The trench region generates thousands of earthquakes every year, ranging from tiny tremors that can only be detected by sensitive instruments to massive magnitude 8+ events that can be felt across the entire Pacific Basin. By deploying networks of sensitive seismic instruments, both on the seafloor and in the deep ocean itself, scientists have created an unprecedented window into the earthquake generation process. These monitoring systems can detect earthquakes as they're happening and track how seismic waves travel through the Earth's interior, providing real-time insights into the structure and dynamics of our planet's deep layers. But here's what makes the Mariana Trench particularly valuable for seismic research. The extreme depth of the subduction zone means that earthquakes occur at depths that are impossible to study in most other tectonic settings. Deep earthquakes, those occurring at depths of 300–600 kilometers or more, provide unique information about conditions and processes in the Earth's upper mantle, regions that we can never directly explore. The seismic data from these deep earthquakes has revealed the three-dimensional structure of the subducting Pacific Plate as it descends through the mantle, showing how the plate deforms, breaks apart, and eventually gets incorporated into the planet's interior. This research has practical implications too. By understanding how stress accumulates and is released in subduction zones, scientists are developing better methods for assessing earthquake hazards and tsunami risks throughout the Pacific Ocean. The monitoring networks around the Mariana Trench have already provided early warning of several major earthquakes and tsunamis, potentially saving thousands of lives around the Pacific Rim. Recent advances in underwater seismic monitoring technology have made it possible to detect and analyze earthquake precursors, subtle changes in seismic activity that might occur before major earthquakes, opening up the possibility of more reliable earthquake prediction in the future. Here's where things get absolutely mind-blowing. Research in the Mariana Trench is providing crucial insights for astrobiology and the search for life elsewhere in the universe. The extreme conditions in the trench, crushing pressure, complete darkness, extreme temperatures, and toxic chemicals are similar to conditions that might exist on other planets and moons in our solar system and beyond. The discovery of thriving ecosystems around hydrothermal vents in the trench has revolutionized our understanding of life's limits and demonstrated that complex organisms can survive and reproduce in environments that would have been considered completely hostile just a few decades ago. This research is directly relevant to the search for life on places like Europa, Jupiter's ice-covered moon, which likely has a subsurface ocean with hydrothermal vents similar to those found in the Mariana Trench. The extremophile organisms discovered in the trench represent some of the most pressure-tolerant, temperature-resistant, and chemically tolerant life forms known to science, expanding our understanding of the habitable zone, the range of conditions under which life might be possible. Some of the metabolic pathways used by trench organisms are so unusual that they provide entirely new models for how life might exist in environments completely different from Earth's surface. The discovery of organisms that can derive energy from chemical processes rather than sunlight has shown that life doesn't necessarily require a nearby star to survive, opening up the possibility that life could exist in the cold, dark environments of rogue planets or the subsurface oceans of icy moons. NASA and other space agencies are actively using the Mariana Trench as a testing ground for instruments and techniques that might be used to search for life on other worlds. The challenges of operating equipment under extreme pressure and in corrosive environments are similar to those that would be encountered on missions to explore the oceans of Europa or Enceladus, making the trench an ideal Earth-based analog for these alien environments. Now, here's something that could have profound implications for human health. The unique organisms living in the Mariana Trench are becoming a source of new medical and pharmaceutical discoveries that could revolutionize treatment for various diseases. The extreme conditions that these organisms have adapted to have driven the evolution of unique biochemical compounds and cellular processes that don't exist anywhere else in nature. Many of these compounds have properties that make them potentially valuable for medical applications. For example, the pressure-resistant enzymes found in deep-sea organisms remain stable and functional under conditions that would destroy normal proteins, making them potentially useful for medical applications that require high stability and durability. Some deep-sea bacteria produce antibiotic compounds that are effective against drug-resistant pathogens, offering hope for treating infections that don't respond to conventional antibiotics. The unique proteins found in deep-sea organisms are also being studied for their potential use in drug delivery systems, medical imaging, and tissue engineering. Researchers have discovered that some deep-sea organisms produce compounds with anti-inflammatory, anti-cancer, and neuroprotective properties that could lead to new treatments for a wide range of diseases. The bioluminescent chemicals produced by deep-sea creatures are already being used in medical research and diagnosis, allowing scientists to track biological processes in living tissues with unprecedented precision. But perhaps most importantly, the study of how organisms survive and thrive under extreme stress conditions is providing new insights into cellular repair mechanisms, stress resistance, and longevity that could have applications for treating age-related diseases and extending healthy human lifespan. Some deep-sea organisms live for hundreds or even thousands of years while maintaining cellular function and avoiding the accumulation of damage that normally accompanies aging, suggesting that they've evolved mechanisms for cellular maintenance and repair that could potentially be applied to human medicine. The pharmaceutical potential of deep-sea organisms is so significant that several major drug companies have established research programs specifically focused on discovering and developing compounds from extreme environment organisms. Here's something that really ties together all the research we've discussed. The Mariana Trench has become a natural laboratory for studying how Earth's systems interact and influence each other on a global scale. The discoveries made in this remote location are helping scientists understand connections between the deep ocean, the atmosphere, the solid Earth, and the biosphere that were previously unknown. For example, research on deep-sea carbon cycling has revealed that the ocean's deepest places play a much more important role in global climate regulation than anyone previously realized. The discovery of ancient water masses in the trench has provided new insights into how ocean circulation affects global weather patterns over timescales of centuries and millennia. The study of deep-sea ecosystems has shown how life in the most extreme environments can influence global biogeochemical cycles, affecting everything from oxygen levels in the atmosphere to the chemistry of seawater around the world. The geological research has revealed how processes deep within the Earth affect surface conditions, showing that the planet operates as a single, integrated system, where changes in one component can have effects that propagate throughout the entire system. This systems-level understanding is crucial for predicting how Earth will respond to ongoing environmental changes and for developing strategies to address global challenges like climate change, pollution, and biodiversity loss. The Mariana Trench research is also demonstrating the importance of protecting deep-sea environments, not just for their own sake, but for their role in maintaining the stability and health of the entire planet. As we continue to explore and study this remarkable place, we're gaining a deeper appreciation for the interconnectedness of Earth systems and the crucial role that even the most remote and extreme environments play in supporting life on our planet. Finally, as we wrap up our journey through 100 facts about the deepest place on Earth, it's worth reflecting on how the Mariana Trench represents both the ultimate frontier for exploration and a crucial key to understanding our planet's future. Every dive, every sample collected, and every measurement taken in this remote location adds to our growing understanding of how Earth works as a complete system. The discoveries made in the Mariana Trench are helping us address some of the most pressing questions facing humanity. How will our climate change in the coming decades and centuries? What are the limits of life, and how might life exist elsewhere in the universe? How can we develop new medicines and technologies by learning from nature's most extreme adaptations? How can we protect and preserve the health of our planet's oceans for future generations? The research continues at an accelerating pace, with new technologies making it possible to study the trench in greater detail than ever before. Each expedition reveals new species, new geological features, and new insights into the processes that shape our planet. The Mariana Trench serves as a reminder that despite all our technological advances and scientific knowledge, our planet still holds countless mysteries waiting to be discovered. As we've learned throughout this exploration of 100 facts, the deepest place on Earth is far more than just a geographical curiosity. It's a window into our planet's past, a key to understanding its present, and potentially a guide to securing its future. The tiny submersibles that carry brave explorers into this alien world return with discoveries that could change how we live, how we treat disease, and how we protect our environment. In many ways, the Mariana Trench represents the perfect metaphor for scientific discovery itself, a deep, mysterious place that rewards careful exploration with profound insights that can benefit all of humanity. If you enjoyed our video today, subscribe to our channel